The countdown has begun. What if the worst-case scenario is already unfolding with 3 Atlas according to the data we have today? 3 Atlas appears to be a natural object. The observations point toward ice, dust, and the familiar behavior of a comet entering our solar system. But at the edges of that explanation, in the quiet space where speculation begins, a darker possibility slowly takes shape. What if the story is not as simple as a comet passing through and leaving again? What if it is not leaving at all? What if the trajectory we interpret as an exit is something else entirely? Imagine, for a moment, a probe so advanced that it could imitate nature perfectly, disguising itself as nothing more than a drifting mixture of ice and dust. Indistinguishable from an ordinary comet moving through the darkness of space. Imagine a civilization so cautious that it does not send messages and does not attempt contact. Instead, it sends watchers, silent observers that never reveal themselves, never interfere, and simply study the worlds they pass. If such a possibility were real, then 3 Atlas would not merely be a wandering rock from another star system. It could be a signal, or perhaps something far more unsettling. A test. Tonight we will explore the fragile boundary between science and speculation. We will follow the evidence that astronomers have gathered and examine why the 29th of October may become the moment when this object reveals its true nature. We will weigh the natural against the unnatural, the science against the suspicion, comfort against unease, and ask a question that is both simple and deeply unsettling. Is the worst-case scenario already happening? On the night of the 1st of July 2025, what began as a routine sky survey quietly turned into a moment that would be recorded in the history of astronomy. At an observatory in Chile, the Atlas telescope system, built primarily to search for asteroids that might one day threaten Earth, was scanning the sky as it does every clear night. Its cameras constantly watch for faint points of light that drift slightly against the fixed background of distant stars. Most of these moving specks turn out to be ordinary asteroids or comets, objects that have been circling the sun for billions of years. But that night, one tiny point of light behaved just differently enough to demand attention. At first it seemed unremarkable. A dim object around magnitude 14. Faint, but still within the reach of modern survey telescopes. Slowly shifting across the detector, the automated software flagged it for routine follow-up. Just another entry in the endless catalogue of small bodies that astronomers track every week. Thousands of these objects are discovered every year, and most quickly fade into the background of astronomical databases. But as more observations arrived and astronomers began refining its orbit, the numbers started to behave in a way that no one expected. Objects bound to the sun follow predictable paths. Asteroids trace graceful ellipses that repeat over years or centuries. Comets stretch those ellipses into long, dramatic loops that carry them far into the outer solar system before gravity draws them back again. Even the most extreme comet orbits still remain tethered to the sun, confined within the vast gravitational architecture of our planetary system. But this object refused to fit that pattern. With every new observation, its calculated trajectory drifted farther away from any bound orbit. Instead of closing into an ellipse, the curve continued to open outward. The mathematics eventually became impossible to ignore. The path was not elliptical at all. It was hyperbolic, the unmistakable signature of an object that is not gravitationally bound to the sun. In celestial mechanics, a hyperbolic trajectory means only one thing. The object did not originate here. It was passing through our solar system only once, arriving from the depths of interstellar space before continuing its journey back into the darkness between the stars. Within hours, the realization began spreading through the global network of observatories. Messages moved rapidly between research groups. Orbital calculations were repeated and checked again and again. Independent measurements from different telescopes confirmed the same astonishing conclusion. For only the third time in recorded human history, astronomers had detected an interstellar visitor crossing our solar system. The object was soon given its provisional designation, 3I Atlas, the third known interstellar object ever discovered, and named after the Atlas survey system that first detected it. The announcement quickly rippled through the scientific community and then into the public sphere. Journalists and science writers immediately reached for comparisons. The mysterious visitor, Oumuamua, that surprised the world in 2017, the comet Borisov that followed 2 years later in 2019, both had arrived silently from the interstellar void, offered only brief glimpses of their nature, and then disappeared forever into deep space. Now, a third messenger had arrived, and once again the solar system found itself briefly connected to the wider galaxy beyond. But almost immediately, astronomers noticed that something about this visitor felt different. Its speed was unusually high. Its brightness seemed stronger than expected for an object at that distance. And the earliest spectroscopic hints of its chemistry suggested a composition that scientists had rarely seen before. From the moment it was detected, 3 Atlas carried with it a sense of mystery that seemed heavier than the icy nucleus drifting through space. In those first days, before headlines spread and speculation began to grow, there was only the quiet astonishment of discovery. A faint point of light on a detector had suddenly connected us to the immense machinery of the galaxy. Somewhere far beyond our solar system, perhaps around a star we may never identify. Gravitational forces had once hurled this fragment outward into interstellar space. For millions, or perhaps billions of years, it had wandered through the darkness unseen. Only by extraordinary coincidence did its path eventually intersect with the small field of view of a telescope on a mountain in South America, bringing it for the first time into human awareness. The discovery of 3 Atlas did not arrive with fireworks or dramatic flashes across the sky. There were no sudden lights visible to the naked eye, and no spectacular celestial display announcing its presence. Like many of the most important discoveries in modern astronomy, it emerged quietly inside streams of digital data, a whisper hidden within numbers. Yet inside that whisper was the beginning of a story that might stretch our imagination farther than we expected. Because every interstellar object raises the same unsettling question. What else drifts through the vast spaces between the stars? And how many of those travelers pass through our solar system without ever being noticed? The confirmation of this visitor came not through excitement or speculation, but through careful measurement, numbers that were calm, precise, and impossible to ignore. Over the next 2 nights in early July 2025, observatories across the world turned their telescopes toward the faint intruder first glimpsed by the Atlas survey. Each new observation refined its orbit and strengthened the extraordinary conclusion that this was not a native object of our solar system, but a traveler from another star. Each telescope added new points to the growing map of its trajectory. And with every new measurement, the picture became clearer. The orbits simply refused to close. Gravity could not capture it. What had first appeared to be a distant comet slowly revealed itself as something far stranger. An object moving too fast and along a path too straight to belong to our solar system. The calculations spread quickly through the scientific community. In observatories, data centers, and control rooms around the world, astronomers watched their models update in real time. Elliptical solutions gradually gave way to a curve that opened outward without limit. At the center of this realization was a single number that defines the nature of an orbit. Its eccentricity. If the value is less than 1, the object is gravitationally bound to the Sun. If it equals 1, the path is parabolic, balanced exactly on the edge between capture and escape. But if the number rises above 1, the orbit becomes hyperbolic. The object is not bound to the Sun at all. With each new observation, that number crept higher. First 1.01, then 1.1, then higher still as the data improved. Anything above 1 means the object is moving at escape velocity, destined never to return to the Sun. By the morning of the 3rd of July 2025, the conclusion had become unavoidable. The orbit was hyperbolic. This was an interstellar visitor. For only the 3rd time in human history, the solar system had received a traveler from beyond its boundaries. The first, Oumuamua, had appeared in 2017. Slender, enigmatic, and gone before we could fully understand it. 2 years later came Borisov, a comet unmistakably familiar in its behavior, yet still a foreigner from another star. And now 3 Atlas joined their ranks, carrying with it the promise of new discoveries and new questions. For astronomers, the realization brought both excitement and a quiet sense of unease. Discovering one interstellar object had once felt like extraordinary luck. Discovering 3 within less than a decade suggested something deeper about the nature of our galaxy. Perhaps interstellar space is not as empty as we once believed. Perhaps countless fragments from distant star systems wander endlessly through the Milky Way, slipping silently between the stars. If 3 had already been discovered almost by chance, how many others had passed unnoticed through our cosmic neighborhood? How many had crossed our skies at times when no telescope happened to be watching? Press releases and scientific announcements attempted to capture the significance of the discovery, but the language always felt slightly inadequate. Because behind the calm precision of those orbital calculations was a realization that stretched far beyond a single comet. It hinted at a galaxy filled with wandering relics of distant planetary systems, drifting through the darkness for millions or even billions of years before briefly crossing our path. A fragment from another planetary system had entered our own. Its icy body may have formed around a distant star billions of years ago, before being violently ejected during some ancient gravitational encounter with a massive planet. From that moment on, it began an exile that lasted for unimaginable lengths of time. For millions, perhaps billions of years, it drifted between the stars, carrying within it the chemical fingerprints of its birthplace. Only by chance did that long, silent journey eventually intersect with the instruments of Earth, allowing it to leave a brief mark in the records of human science. There is something deeply humbling in that realization. Our planet had become, however briefly, a waypoint in a journey that began long before humanity existed and will continue long after our civilization is gone. The object itself carried no awareness and no intention. It possessed only momentum, a silent traveler preserving an ancient memory locked inside ice, dust, and frozen gases. And yet its presence inevitably pushes us to look outward and ask more difficult questions. What histories are carried by these wandering fragments from distant star systems? What chemical stories are hidden inside their frozen interiors? And perhaps even more unsettling, what stories might they carry away about us as they pass through our cosmic neighborhood? Silent witnesses to a brief flicker of civilization on a small blue world. In the earliest hours after its discovery, the object possessed nothing more than a provisional label, a sterile string of numbers and letters automatically assigned by the software that tracks newly detected celestial bodies. C 2025 N1, a designation designed purely for cataloging, placing the object neatly within the taxonomy used for comets and asteroids. But once its trajectory was confirmed to be interstellar, that cold catalog number began to feel strangely inadequate. An object that had crossed the immense distances between stars seemed to deserve something more than a line in a database. It deserved a name that reflected both its rarity and its significance in the story of human discovery. The International Astronomical Union followed the convention established by earlier discoveries. The first confirmed interstellar object, Oumuamua, discovered in 2017, had been given a name derived from the Hawaiian language. It can be translated loosely as a messenger arriving from afar. A fitting description for the first known visitor from another star system. 2 years later, the second interstellar object, Borisov, received the formal designation 2I Borisov. Acknowledging both its status as the second known interstellar visitor and the amateur astronomer who discovered it. Now this new wanderer received its place in the sequence. 3I, the third interstellar object ever confirmed. The rest of the name followed naturally. Atlas, the survey system whose digital eyes first detected the faint moving point of light on the 1st of July, was honored in the second half of the designation. Together they formed the name 3I Atlas. It was a simple label. Yet the transformation was immediate. What had once been a sterile string of numbers now carried meaning and narrative weight. Scientists could refer to it easily in conversation. Journalists could build headlines around it. And the public could imagine it as something more than a line of orbital data moving across a computer screen. The name became a container for the story itself. Language has always shaped the way humans relate to the cosmos. Ancient civilizations mapped the stars into constellations filled with hunters, gods, lovers, and monsters. Those names guided how generations interpreted the night sky. Even today, a technical designation can suddenly evoke wonder when it becomes attached to the right discovery. Calling this object, Atlas placed it into a growing lineage of cosmic messengers, each one representing more than a fragment of rock and ice drifting through space. Each interstellar visitor becomes a reminder that our solar system is not isolated. It is connected to the wider galaxy through the slow exchange of material that drifts between the stars. Fragments from distant planetary systems wander for millions or billions of years before occasionally passing through our cosmic neighborhood. The name Atlas also carried an unintended echo from mythology. In Greek legend, Atlas was the Titan condemned to hold up the heavens. That mythological association subtly made the object feel larger than life. In online forums and late-night discussions, some people began referring to it as the third messenger, as though the universe itself were sending a sequence of signals across time. First came Oumuamua, then Borisov, and now Atlas, arriving faster and showing chemical hints that appeared slightly different from its predecessors. To scientists, this was not escalation, but opportunity. Each new interstellar object offers a rare chance to study material formed around another star. Their compositions preserve clues about planetary systems far beyond our own. Yet the human imagination naturally builds stories around them, because names have a way of anchoring discoveries in memory long after the objects themselves have disappeared. Oumuamua has long since faded beyond the reach of our telescopes. Borisov eventually broke apart into a cloud of dust as it passed through the inner solar system. And 3I Atlas will also vanish one day into the darkness beyond the planets. But the names remain. They become markers in the timeline of human exploration. Reference points in the growing story of how our species first began to notice travelers from other star systems. This latest designation, born from the practical needs of astronomical cataloging, is already undergoing that transformation. 3I Atlas is not merely a comet moving along a hyperbolic trajectory. It is a reminder that our solar system is part of a much larger cosmic network, a place where fragments of distant worlds occasionally pass through, carrying silent evidence of the processes that shape planetary systems across the galaxy. And perhaps the most fascinating shift happens once a name begins to circulate widely enough. An object that was once only a discovery slowly becomes part of a shared narrative. 3I Atlas is still just a small body of ice and dust traveling through space. Yet in a cultural sense, it has already crossed another boundary. It has entered our story. The first wave of reports arrived quickly, as they almost always do when a new object enters the astronomical record. 3I Atlas was classified, described, and placed neatly into the familiar category of comet. Early images revealed a faint halo of gas and dust surrounding the nucleus. The telltale coma that forms when sunlight begins to warm frozen ices on the surface. Despite its unusual origin, the object appeared to behave in ways astronomers already understood. Its orbit, though extraordinary in origin, remained predictable. Calculations showed that the object would pass safely through the inner solar system at a distance of roughly 270 million kilometers from Earth. Close enough for detailed study, yet comfortably far from any possibility of danger. The official language used by space agencies reflected that calm assessment. There was no threat to our planet, no dramatic event approaching, only a rare comet that happened to have formed around another star. NASA's early statements carried an almost audible sense of relief. Yes, the object was unusual. Yes, it was moving faster than most comets typically observed. But its path posed no risk to Earth, and its behavior appeared broadly consistent with cometary activity. Scientists emphasized that this was a scientific opportunity rather than a cause for alarm. Journalists largely echoed that tone. Reporters and science writers were careful not to encourage unnecessary speculation. Interstellar visitors have a history of igniting public imagination far beyond what the available evidence supports. When Oumuamua appeared in 2017, some voices quickly suggested it might be an artificial object or an alien probe. Yet as the data accumulated, it simply slipped away from the solar system, leaving behind debates rather than proof. 2 years later, Borisov arrived and behaved exactly like a classic comet, complete with a visible tail and familiar chemical signatures. Its ordinary behavior reassured astronomers that at least some interstellar visitors resemble the comets we already know. 3I Atlas initially seemed likely to follow that same pattern, another unusual but understandable object that would be observed carefully, studied intensely for a short time, and then gradually fade from view as it continued its journey back into the darkness between the stars. For the public, the early narrative was simple and comfortable. A comet, a traveler from another star system, certainly, but still recognizable within the framework of known science. Something that could be explained, categorized, and understood without introducing deeper uncertainty. The headlines leaned into wonder rather than worry. Third interstellar traveler discovered. Cosmic messenger from afar. A harmless visitor passing briefly through our solar system. It was the kind of story that invites curiosity without demanding fear. A reminder of the immense scale of the universe and the countless objects moving silently through it. For a moment, humanity could simply marvel at the fact that a fragment of another planetary system had wandered into our cosmic neighborhood, offering a rare opportunity to glimpse material formed around a distant star. Astronomers also found reassurance in how familiar the object initially appeared. The coma expanded gradually as expected, responding to the increasing warmth of sunlight. The light curve, though faint, remained within the range typically seen in cometary activity. Radio observatories detected no unusual emissions, further reinforcing the early interpretation that this was a natural object behaving much like other comets. Spectroscopic observations from telescopes in Chile, Hawaii, and Spain revealed the presence of carbon dioxide along with fine dust particles. The proportions were somewhat unusual compared with comets native to our solar system, but not beyond the boundaries of known chemistry. Variations in composition are expected when studying material formed around distant stars. For a short time, it seemed that 3I Atlas would behave exactly as an interstellar comet should, offering scientists a rare but straightforward opportunity to examine matter from another planetary system. Yet beneath those early impressions there remained a quiet sense of curiosity. The object's velocity was noticeably higher than that of the previous interstellar visitors we had detected. Its chemical balance did not perfectly match the patterns commonly seen in comets formed within our own solar system, and its trajectory approached the solar system from an angle somewhat tilted relative to the galactic plane, hinting that its origin might lie in a region of the galaxy very different from our own stellar neighborhood. These details were mentioned in scientific discussions, but rarely emphasized in early public reports. They appeared in the appendices of press releases and in the technical sections of research papers. To the broader public, the message remains simple and reassuring. 3I Atlas was harmless. A natural interstellar comet. Another fascinating but ultimately ordinary visitor passing through our solar system. But scientists who follow these discoveries closely know how quickly an apparently ordinary object can become puzzling once more detailed data begins to arrive. Early interpretations in astronomy often change as additional measurements refine the picture. What appears simple at first sometimes becomes more complex as the evidence accumulates. From the beginning, space agencies were careful about how the discovery was communicated. Whenever the phrase interstellar object appears in headlines, the public imagination tends to move faster than the science itself. Speculation can easily grow far beyond what the data supports. For that reason, the earliest official statements were written in the language of precision and calm. There was no threat to Earth. Officials emphasized the closest approach of 3I Atlas would occur at a distance of about 1.8 astronomical units, nearly twice the distance between Earth and Mars. Numbers like these help anchor the discussion in measurable reality. They provide context and perspective. In measured tones, scientists explain not only what the discovery meant, but also what it did not mean. The object was not on a collision course with Earth. It was not a planet-destroying body. And despite occasional speculation in online discussions, there was no evidence that it represented anything artificial. According to the data available at the time, 3I Atlas was simply a natural comet formed around another star, now passing briefly through our solar system before continuing along its hyperbolic trajectory back into the vast interstellar darkness. The early briefings emphasized continuity and experience. NASA had encountered interstellar visitors before. Oumuamua had passed through the solar system in 2017 and left without incident. Borisov followed in 2019, behaving like a typical comet before fading from view. According to the models, 3I Atlas would follow the same pattern. The mathematics of celestial mechanics was well understood. Orbital calculations are among the most reliable tools in astronomy, and the equations showed no path that brought the object anywhere near Earth. For many observers, the tone of those briefings sounded almost like a quiet reassurance delivered in the language of science. Numbers replaced speculation. The eccentricity of the orbit was clearly greater than 1, confirming that the object was not gravitationally bound to the Sun. It's perihelion. The point of closest approach to the Sun would occur at roughly 1.4 astronomical units. Its trajectory had already been mapped far into the future, and there was no indication of any sudden deviation that might bring it toward Earth. Officials repeated the same message in different forms. This was an opportunity for scientific study, not a hazard. The object would remain at a comfortable distance from our planet and would not approach close enough to trigger any planetary defense response. Observatories would observe it, analyze its composition, and learn what they could before it continued its journey back into interstellar space. Still, the confidence of those statements carried an interesting quality of its own. The certainty was strong because the calculations supported it. But in astronomy, certainty always exists within the limits of the available data. As more observations accumulate, details sometimes change and interpretations evolve. Some aspects of 3I Atlas quietly attracted scientific curiosity even in those early days. The spectral data suggested a relatively strong carbon dioxide signature compared with many comets native to our solar system. Its velocity through the solar system was also noticeably higher than that of the earlier interstellar objects we had observed. Neither detail contradicted known physics, but both made the object scientifically interesting. Another point of discussion within the research community was the direction from which the object approached the solar system. Its incoming path appeared somewhat inclined relative to the galactic plane. The broad disk in which most stars in our galaxy orbit That orientation hinted that the object might have originated in a region of the Milky Way populated by older stars and ancient planetary systems. If so, it could be carrying material formed in environments very different from our own. These details were not hidden, but they were technical points more relevant to research papers than to daily news reports. For the general public, the essential message remained simple and accurate. 3I Atlas posed no threat to Earth. The solar system would continue its quiet routine while this interstellar traveler passed through and moved on. And yet, discoveries like this naturally invite deeper questions. Each interstellar object provides a rare opportunity to study matter from another star system directly. The more we learn about them, the more we refine our understanding of how planetary systems form and evolve across the galaxy. In that sense, the real significance of objects like 3I Atlas is not danger or drama, but the knowledge they can offer. In astronomy, speed is often one of the first clues that an object has come from far beyond our solar system. Interstellar visitors tend to arrive with velocities that reflect the motion of stars within the galaxy itself. Measuring that speed allows astronomers to reconstruct parts of the object's past trajectory and estimate how long it may have wandered between the stars before crossing our path. In astronomy, motion is a form of memory. The way an object travels through space can reveal where it has been, what forces have shaped its journey, and what events may have marked its past. With 3I Atlas, the numbers told a story that photographs alone could not capture. The object was moving through the solar system at roughly 61 kilometers per second, more than 130,000 miles per hour. That velocity made it significantly faster than the previous interstellar visitors we had detected, noticeably exceeding the speeds measured for both Oumuamua and Borisov. At first, this detail was treated simply as another interesting feature of the discovery. Interstellar space is vast and dynamic, and objects that are ejected from their birth systems can carry enormous momentum. When planets form around young stars, gravitational encounters between massive worlds can fling smaller bodies outward with tremendous speed. Over billions of years, those fragments drift through the galaxy until chance occasionally brings them through another planetary system. Even so, the velocity of 3I Atlas attracted attention as astronomers began running more detailed simulations. The object had not simply drifted into the solar system. It had arrived moving extremely fast relative to the Sun. That speed is still well within the range allowed by known astrophysical processes. But it encouraged scientists to consider what kind of past journey might produce such momentum. One possibility is that the object experienced multiple gravitational encounters during its long history. Passing near several stars over millions of years could gradually increase its velocity, much like a sequence of gravitational slingshots. In that scenario, the object's present speed would be the cumulative result of many interactions spread across vast stretches of time. Another possibility concerns its origin within the structure of our galaxy. Most stars, including the Sun, orbit within what astronomers call the thin disk of the Milky Way. But there also exists a thicker stellar population known as the thick disk, containing older stars with somewhat different orbital dynamics. If 3I Atlas originated in such an environment, the gravitational conditions there could help explain why it now travels with a relatively high velocity compared with objects born closer to the Sun's galactic neighborhood. These ideas remain active areas of research, because each interstellar object provides only a brief observational window before it disappears again into deep space. Astronomers therefore try to reconstruct as much of the object's past as possible using orbital mechanics and statistical models of stellar motion. During earlier discoveries, similar discussions occasionally expanded into more speculative territory. When Oumuamua passed through the solar system, Harvard astronomer Avi Loeb proposed the possibility that its unusual acceleration might resemble the behavior of a very thin object pushed by radiation pressure from starlight. That interpretation, sometimes described as a light sail hypothesis, was widely debated but ultimately not supported by the majority of observational evidence. Most researchers concluded that natural explanations involving outgassing or other physical processes were sufficient. With 3I Atlas, the conversation returned to more familiar scientific ground. Its velocity, while high, can still be explained through known gravitational interactions, operating over long cosmic timescales. NASA and other research institutions emphasized that point clearly in their communications. Natural astrophysical mechanisms remain fully capable of producing the speeds we observe in objects traveling through the galaxy. The laws of physics remain valid even at 61 kilometers per second. Yet, among researchers, there was an unspoken awareness that velocity is one of the hardest properties of an object to reinterpret. Shape can be misleading. Chemistry can surprise us. But speed is a direct consequence of energy and motion. Something in the distant past of this object had accelerated it to a pace few scientists had expected for an interstellar visitor. And now it was already crossing our solar system with remarkable precision. The challenge with speed is not only what it reveals about the past, it also determines what happens next. At a velocity like this, 3I Atlas cannot be captured by the Sun's gravity. It will not settle into a long orbit around our star. Instead, it will sweep through the solar system only once, briefly revealing its nature before continuing its journey back into interstellar space. Humanity has only a short observational window to study it before it disappears forever. Because of that limited opportunity, some of the most powerful telescopes available were quickly directed toward the object. Among them was the James Webb Space Telescope, whose instruments are capable of analyzing the chemical fingerprints of distant objects with extraordinary sensitivity. When its mirrors were turned toward 3I Atlas, astronomers expected to refine what they already suspected about its composition. Spectroscopy normally provides clarity by separating light into precise molecular signatures that reveal the presence of specific gases and ices. What the data suggested, however, attracted immediate scientific attention. The early spectra indicated that the coma surrounding the object contained a strong signal from carbon dioxide. In many comets, carbon dioxide is present, but typically in smaller proportions compared with water vapor, which is usually the dominant component driving comet activity near the Sun. On Earth, carbon dioxide is a familiar molecule. It is part of our atmosphere and an important component of the planet's climate system. In comets, however, water ice is usually the primary material that vaporizes as sunlight warms the nucleus. That vaporization process creates the glowing halo, or coma, that we observe around active comets. If the measurements for 3I Atlas are confirmed, they would suggest that carbon dioxide may play a more significant role in driving its activity than is typical for many comets formed in our own solar system. Such a composition would not violate any physical laws. Instead, it would provide valuable information about the conditions under which the object originally formed around its parent star, offering another clue about the diversity of planetary systems across the galaxy. Until the data from the James Webb Space Telescope began to settle, the first reaction inside the research community was disbelief. When an unexpected signal appears in spectroscopy, the safest assumption is that something in the measurement process may be wrong. Instruments can drift. Calibration can shift. Data pipelines can introduce subtle artifacts. So the teams did what astronomers always do in those moments. They checked everything again. The spectra were reprocessed. Calibration files were verified. Independent instruments were consulted. Yet with each repetition, the same pattern continued to appear. The signal remained consistent. The ratio held. The coma surrounding 3I Atlas appeared to contain an unusually strong presence of carbon dioxide compared with water vapor. For scientists, this was not alarming. But it was intriguing. Interstellar objects formed in environments very different from our own solar system, and their chemistry may reflect those distant conditions. Several explanations quickly emerged. One possibility is that the object formed near the carbon dioxide snowline of its parent star system, the region where temperatures are low enough for carbon dioxide to freeze directly into solid ice. In such a location, the material that eventually formed the comet could naturally contain a higher proportion of carbon dioxide relative to water. Another hypothesis considers the effects of cosmic radiation over extremely long timescales, during millions or billions of years drifting through interstellar space. Energetic particles can chemically process the surface layers of icy bodies. That radiation may alter the balance of volatile materials, potentially trapping some compounds beneath the surface while allowing others to escape more easily when the object approaches a star. A third possibility involves the physical structure of the nucleus itself. Some comets develop insulating layers of dust over time. Such a mantle can shield deeper water ice from direct heating while allowing more volatile compounds such as carbon dioxide to seep outward through fractures and pores in the surface. In that scenario, the unusual gas signature would reflect how the material is distributed inside the nucleus rather than the overall composition of the object. Each of these explanations fits within known comet physics. Yet the combination of details made 3I Atlas scientifically fascinating. One particularly interesting factor was the distance at which the activity was detected. At more than 3 astronomical units from the Sun, many comets in our solar system remain relatively quiet because the sunlight is still weak compared with the inner regions near Earth and Mars. Yet this object was already releasing gas and forming a detectable coma. Publicly, NASA described the chemistry in measured and cautious terms. The composition was unusual, but not impossible. In fact, it represented a valuable opportunity. Interstellar visitors like 3I Atlas preserve materials formed around other stars, offering scientists a rare chance to examine the chemical environments that exist elsewhere in our galaxy. In that sense, the discovery was not a problem to solve, but a window into planetary systems far beyond our own. Publicly, the unusual chemistry was framed as an exciting scientific puzzle. But within research discussions, some scientists quietly wondered about the deeper implications of what they were seeing. Why would this object contain such a strong carbon dioxide signal compared with typical comets? Why would its activity begin so early, far from the Sun, where most cometary bodies remain relatively inactive? And why was this particular object arriving now, at this moment in human observation? These questions naturally arise whenever astronomers encounter something unexpected. Interstellar objects are rare, and each new discovery forces scientists to revisit assumptions about how planetary systems form and evolve. Most researchers view the unusual chemistry simply as evidence that 3I Atlas formed in a very different environment from the one that created our solar system. Different stars, different temperatures, and different protoplanetary disks can produce objects with compositions that look unfamiliar to us. Still, the human mind is always drawn toward interpretation when confronted with mystery. Throughout the history of astronomy, unusual discoveries have occasionally inspired more speculative ideas before the data eventually settles into a clearer explanation. Such speculation rarely survives careful analysis, but the questions themselves can sometimes guide new research and observations. In the case of 3I Atlas, the chemistry puzzle did not immediately produce a single satisfying answer. Instead, it expanded the list of possibilities astronomers were considering. The object was already unusual in several ways. It was moving faster than earlier interstellar visitors. Its incoming trajectory suggested a potentially different galactic origin, and its chemical signals hinted at a composition that did not closely resemble many comets observed in our own solar system. As the object continued its inward journey toward the Sun, scientists knew that the coming months would provide more data. Additional observations would allow them to track how its activity evolved as sunlight increased, offering new clues about the structure of the nucleus and the materials trapped inside it. For researchers studying interstellar objects, the story of 3I Atlas was only beginning. One of the next steps involved listening as well as watching. Space may appear silent to human senses, but in reality it is filled with electromagnetic activity. Stars emit radiation across the spectrum. Planets interact with solar winds. Comets themselves can produce faint radio signatures as gas and dust interact with charged particles from the Sun. Because of this, radio telescopes were directed toward 3I Atlas to see whether the object produced any detectable signals. Astronomers were not expecting anything unusual, only the faint radio noise that sometimes accompanies comet activity. Observatories searched for narrowband emissions, repeating patterns, or any unusual signals hidden within the background radio spectrum. What they found was reassuringly ordinary. The object produced no artificial transmissions, no structured signals, and nothing that suggested technological origin. Instead, the data showed only the quiet electromagnetic background expected from a natural comet. For scientists, this result reinforced the simplest explanation. 3I Atlas behaved exactly like an interstellar comet should when observed in radio wavelengths. The absence of unusual signals became another piece of evidence supporting the interpretation that the object was natural. In discussions about the search for extraterrestrial intelligence, silence itself is often an important theme. Space appears quiet not because nothing exists beyond our world, but because detecting distant civilizations would require signals that travel across enormous cosmic distances. The fact that we detect no such signals from an object like 3I Atlas simply reflects the reality that most astronomical bodies, even those born around other stars, are exactly what they appear to be: natural fragments of distant planetary systems traveling through the galaxy. If 3I Atlas was somehow artificial, one might imagine that the most effective disguise would be simplicity. An object that looks and behaves like a comet, emitting nothing more than the faint hiss of gas and dust, would slip easily past even the most attentive observers. It would not draw attention. It would blend perfectly into the countless natural bodies that move through space. But interpreting silence is always difficult. When radio telescopes examined the object, the data showed nothing unusual. The instruments detected only broad-spectrum background noise, exactly the kind expected from a natural comet interacting with solar radiation and the surrounding plasma of the solar system. There were no narrowband transmissions, no repeating patterns, and no signals that suggested technological origin. For scientists, that result was reassuring. It fit neatly with the simplest explanation that 3I Atlas is a natural interstellar comet. In astronomy, the absence of unusual signals is often an important piece of evidence. Most objects in space are quiet in radio wavelengths, and comets are no exception. Even so, the process of verification was thorough. Radio observatories across the world participated in the search. Large facilities, as well as smaller research instruments, scanned the relevant frequencies, looking for anything that might stand out from the background. The Deep Space Network, along with other radio arrays used in astronomical and SETI observations, contributed to the effort. Each independent dataset reached the same conclusion. 3I Atlas was radio quiet. It was quiet in the same way that natural space debris is quiet. Quiet like ancient ice drifting through interstellar space for millions or billions of years. From the perspective of radio astronomy, the object behaved exactly as a comet should. That conclusion did not diminish the scientific value of the discovery. If anything, it reinforced how extraordinary it is that fragments from other star systems occasionally pass through our solar system. Even when they behave exactly as physics predicts, they still carry information about distant environments we cannot otherwise reach. In the end, the silence surrounding 3I Atlas became part of the story not because it hinted at anything mysterious, but because it confirmed something important. Most visitors from the galaxy arrive quietly. They reveal their secrets not through dramatic signals, but through careful measurements of motion, composition, and light. If something truly wished to remain unnoticed, The most effective disguise would simply be normality. An object that behaves exactly like a comet, emits nothing unusual, and produces only the faint natural signals expected from ice and dust would pass through our instruments without raising suspicion. Silence, in that sense, can sometimes feel almost too perfect, long before chemistry or images reveal their secrets. Trajectories already tell a story. The path of an interstellar object is never random. It is shaped by gravity, a fossil record of countless interactions stretching back across immense spans of time. Every bend and angle in that path carries information about where the object has traveled and what forces have influenced it. When astronomers analyzed the orbit of 3I Atlas, one detail immediately stood out. The direction from which it entered the solar system was unusual. Most objects that pass through our region of space tend to follow the broad motion of the galaxy's thin disk, the flattened structure in which most stars, including our Sun, orbit the center of the Milky Way, 3I Atlas. However, approached from a noticeably different angle, its path appeared tilted relative to the galactic plane, as though it originated from a population of stars with more inclined and eccentric orbits. That geometry naturally led scientists to compare its motion with the Milky Way's thick disk, an older stellar component that surrounds the thin disk and contains stars that formed earlier in the galaxy's history. Stars in the thick disk tend to move along more tilted and irregular paths, reflecting the turbulent conditions that existed when the Milky Way was still evolving. If 3I Atlas truly originated from such a region, the implications would be scientifically fascinating. Objects from the thick disk could carry chemical information from planetary systems that formed billions of years ago, during an earlier phase of galactic history. Studying material from such an environment might reveal details about how planetary formation proceeded in those ancient conditions. The possibility also raises interesting questions about endurance. Small icy bodies drifting through interstellar space must survive exposure to cosmic radiation, collisions with tiny dust particles, and countless gravitational disturbances over enormous spans of time. Yet theoretical models show that objects of this size can indeed persist for billions of years, especially if they spend most of their history traveling through the relatively empty spaces between stars. Orbital simulations have therefore become an important part of the effort to understand 3I Atlas. By tracing its trajectory backward through the galaxy, astronomers attempt to estimate the types of stellar environments it may have encountered along the way. In many cases, such simulations can suggest plausible regions where an object might have been ejected from a planetary system. For 3I Atlas, the reconstruction remains uncertain, which is not unusual for objects that have traveled such vast distances. Over long timescales, repeated gravitational interactions gradually blur the exact memory of an object's birthplace. Instead of pointing to a single star, the trajectory often reflects a long history of encounters scattered across the galaxy. What the orbit does suggest is that this object may have been traveling for an extremely long time before reaching our solar system. If that interpretation is correct, then 3I Atlas could represent a fragment from a very ancient planetary system, preserving chemical traces from an earlier epoch of the Milky Way. In that sense, it is not just an interstellar visitor, but also a messenger from deep galactic history, offering a rare glimpse into environments that existed long before our own solar system formed. For some observers, the unusual angle of approach simply reflected the complex dynamics of the galaxy, but for others it felt strangely distinctive. If an object were entering the solar system without drawing attention, arriving from a direction less aligned with the main flow of stellar motion might naturally make it harder to notice. It would not follow the common paths along which many astronomical surveys already focus their attention. NASA and other institutions consistently emphasize the natural explanations: orbital eccentricity, gravitational scattering across the galaxy, And simple statistical chance can easily produce trajectories that look unusual from our limited perspective. In a galaxy containing hundreds of billions of stars and countless drifting fragments of planetary systems, odd geometries are not only possible, they are expected. Even so, the trajectory of 3I Atlas captured the imagination of those who study such objects closely. It was not threatening, and it did not contradict known physics. But it remained undeniably unusual. A curve drawn across the sky that hinted at a story stretching far deeper into the past than our current models could easily reconstruct. A reminder that every interstellar visitor carries a history far older than the solar system itself. Like every comet, 3I Atlas also had an approaching moment that astronomers call its moment of truth. The point in its orbit when it would pass closest to the Sun. That event, known as perihelion, is when sunlight and heat reveal the true nature of a comet's composition. As the nucleus warms, frozen materials begin to vaporize, releasing gases and dust into space and exposing layers that have remained hidden for millions or billions of years. For 3I Atlas, that moment was calculated soon after its orbit became clear. The date was the 29th of October 2025. Astronomers around the world immediately began preparing for the observations that would follow. Perihelion would be the moment when the object's activity would increase and its internal chemistry would become far easier to study. Observatories began scheduling time months in advance. Large ground-based telescopes would track the growth of the coma as sunlight triggered the sublimation of frozen gases. The Hubble Space Telescope would attempt to capture detailed images whenever the object's position allowed it to observe through the Earth's orbit. The James Webb Space Telescope would focus on spectroscopy, searching for molecular signatures in the expanding cloud of gas surrounding the nucleus. Even amateur astronomers prepared to participate. As the comet brightened, there was a possibility that it might become visible through moderate-sized telescopes from Earth. Enthusiasts around the world hoped to capture images of a faint smudge, gradually growing into a more recognizable comet as it approached the Sun. Excitement spread through the astronomy community, not because anyone expected danger, but because perihelion is often the most revealing phase in a comet's life. Some comets brighten dramatically as fresh material erupts from their surfaces. Others fragment under the stress of rapid heating and violent outgassing, breaking apart into clouds of dust that slowly disperse into space. For 3I Atlas, the anticipation felt especially strong. Its composition already appeared unusual. Its speed and trajectory hinted at a long and complex past. Scientists were eager to see how the object would respond when exposed to the stronger sunlight of the inner solar system after perhaps billions of years wandering through the cold darkness between stars. Some researchers suggested that heating might eventually expose deeper layers of water ice hidden beneath the surface, altering the chemical signals already detected. Others considered the possibility that carbon dioxide would remain the dominant gas, offering an even clearer view of how this object formed around its original star. And as always, the more imaginative corners of public discussion added their own interpretations. Speculation about dormant mechanisms or unknown processes occasionally surfaced in online forums and late-night conversations. Scientists, however, focused on what the data could reveal. Perihelion would provide the answers. And those answers would come not from speculation but from the quiet, patient work of observation. If 3I Atlas were anything more than a comet, then perihelion would be the moment when its disguise could no longer hold. That close passage by the Sun would expose whatever lay beneath its frozen surface. Heat has a way of revealing the true nature of cometary bodies, forcing gases to escape and exposing materials that have remained hidden for vast stretches of time. NASA's public language, however, remained calm and precise. The upcoming perihelion posed no danger to Earth. The object's closest approach to the Sun would occur at roughly 1.4 astronomical units, well outside the orbit of Earth and still near the distance of Mars. From a planetary defense perspective, the event carried no risk at all. Even so, the official statements acknowledged that the object was scientifically unusual. Its chemistry already appeared different from many known comets. Its velocity through the solar system was higher than earlier interstellar visitors, and its origin somewhere beyond our planetary neighborhood made every new observation valuable. As the weeks passed, anticipation quietly grew across the astronomical community. The countdown to perihelion felt less like waiting for an ordinary comet and more like preparing for a rare moment of discovery. Each clear night brought new measurements. Telescopes tracked subtle changes in brightness and activity as the object slowly moved deeper into the sun's gravitational domain. Astronomers refined their instruments and observation schedules. Journalists prepared stories explaining why this interstellar visitor mattered. Even casual skywatchers began asking the same simple question. What will happen when it finally heats up? Because when ancient ice that has spent billions of years in the cold darkness of interstellar space encounters the stronger sunlight of the inner solar system, something almost always changes. Gases trapped deep inside begin to escape. Fissures crack and shift. New material becomes visible for the first time. The real question was not whether 3i Atlas would reveal new information. The question was, what exactly that revelation would be. And the countdown toward that moment had already begun. One of the reasons astronomers initially felt comfortable about the discovery lies in the mathematics of its orbit. A hyperbolic trajectory is straightforward to interpret. The object arrives quickly from interstellar space, curves around the sun once, and then departs again, never to return. It is the cosmic equivalent of a traveler passing briefly through a distant city before continuing onward. That was the reassurance offered when 3i Atlas was first identified. Its orbital eccentricity was greater than 1. Its velocity was too high for the Sun to capture it into a repeating orbit. The geometry of celestial mechanics appeared to have already written its future. Yet when scientists study objects moving through space, speed becomes one of the most important parameters. In orbital mechanics, velocity determines not only where an object is going, but how its path might change under gravitational influence. Even small adjustments in speed can alter the shape of a trajectory over time. For that reason, astronomers continue to measure the motion of interstellar objects with extreme precision. Each new observation refines the model, ensuring that the predicted path remains consistent with the laws of physics that govern every object moving through the solar system. In orbital mechanics, the balance of speed is everything. Move too fast, and an object escapes the gravitational pull of a star forever. Move too slowly, and gravity captures it into a repeating orbit. 3i Atlas currently sits on the side of that balance that leads outward. Its velocity is high enough that the Sun cannot hold it, and the mathematics of its trajectory describes a clean hyperbolic path that will eventually carry it back into interstellar space. This is why astronomers were initially confident in their predictions. The physics governing such motion is well understood. Hyperbolic trajectories are common for objects that originate beyond the solar system. They enter quickly, curve around the Sun once, and then depart again along a new direction, never to return. Still, the dynamics of motion through space often invite deeper curiosity. Gravity is not only a force that accelerates objects. Under the right circumstances, it can also redirect and slow them. Human spacecraft routinely use gravitational assists when traveling through the solar system, borrowing energy from planets to change speed and direction. In principle, the same physical laws apply to natural objects moving through the galaxy. Although the process usually unfolds over enormous spans of time, for 3i Atlas, however, all available measurements indicate that its motion is consistent with a natural interstellar flyby. Each new observation refines the orbital solution and continues to match the predictions of classical celestial mechanics. The trajectory remains hyperbolic and stable, exactly what scientists would expect for an object that originated beyond our solar system. The interesting aspect is how smoothly the path can now be predicted. When astronomers track interstellar objects, they sometimes see small irregularities caused by jets of gas escaping from the surface. These outgassing forces can slightly nudge the object and introduce tiny deviations in the orbit. So far, 3I Atlas has behaved in a remarkably consistent way, making it easier for researchers to model its motion accurately. This predictability allows scientists to forecast its future path with high confidence. The object will continue its journey through the solar system, pass its closest point to the Sun, and then gradually fade as it moves outward again into the deep darkness between the stars. Over time, its brightness will drop below the limits of our telescopes and it will disappear from view, continuing along a path determined long before the solar system itself formed. The real significance of that journey lies not in speculation, but in the rare opportunity to observe such a visitor while it is still close enough to study. Each measurement of its orbit, composition, and activity adds another piece to our understanding of how planetary systems evolve across the galaxy. Interstellar objects like 3I Atlas are reminders that the Milky Way is filled with fragments of distant worlds, wandering quietly through space until chance brings one of them briefly into our view. What if Atlas is not simply a visitor passing through our solar system, but something far more subtle? Not a threat in the dramatic sense we often imagine, not a collision, not destruction, but a quiet arrival, an object that appears to be leaving while in fact it has already begun to stay. Nature, after all, provides the perfect camouflage. In a solar system already filled with millions of comets, asteroids, and fragments of ancient debris, hiding in plain sight would require no invisibility, no exotic technology visible to us, only imitation. Blend into the natural chaos of icy bodies and dusty tails, and even the most sophisticated observers might see nothing unusual. Comets themselves are ideal masks. They are messy objects. Their surfaces fracture under sunlight, releasing unpredictable jets of gas and dust. Their brightness fluctuates. Their chemical signatures vary widely. Some are rich in water ice. Others release carbon monoxide, methane, ammonia, or carbon dioxide. Irregularity is not a flaw in a comet, it is its defining trait. This is why unusual chemistry rarely triggers alarm among astronomers. When an object displays unexpected ratios of gases, the first explanation is almost always natural variation. Comets formed in different regions of their original planetary systems, under different temperatures and pressures. Their compositions reflect those distant birthplaces. 3I Atlas itself shows signs of carbon dioxide dominating its activity more strongly than is typical for many comets observed near the Sun. That is scientifically interesting, but not unprecedented in principle. Interstellar objects may carry chemical signatures shaped by environments very different from those in our own solar system. Still, the thought experiment is difficult to resist. If an advanced civilization ever wished to conceal technology within a natural object, a comet would provide a remarkably convincing disguise. Layers of ice, dust, and regolith would mask any underlying structure. When sunlight warmed the surface, gas could vent naturally, creating the familiar coma and tail astronomers expect to see. Spectrographs would detect ordinary molecules. Telescopes would see nothing more than an irregular chunk of frozen debris shedding material into space. Any small anomalies could easily be attributed to unusual formation conditions in some distant star system. From the outside, nothing would appear fundamentally wrong. Only a faint sense of strangeness would remain, an object behaving just slightly differently from the thousands of comets already catalogued. Of course, there is currently no evidence that 3I Atlas is anything other than a natural interstellar body. Every observation so far fits comfortably within known physics and cometary behavior. But the idea that technology could hide within nature is not a new one in scientific speculation. And that possibility leads to a fascinating question not about Atlas itself, but about our own assumptions. If something truly advanced wanted to pass unnoticed through a young technological civilization's telescopes, would it appear extraordinary, or would it look exactly like another comet? For decades, thinkers in the field of the search for extraterrestrial intelligence have considered a similar possibility. Instead of obvious starships or dramatic signals, advanced civilizations might deploy quiet observers, devices designed to watch rather than announce themselves. Concepts like the Bracewell probe or von Neumann probe imagine machines capable of traveling between stars, studying emerging civilizations while remaining effectively invisible. In those theoretical discussions, the key idea is subtlety rather than spectacle. A truly patient probe would not glow or transmit loudly across the cosmos. Instead, it would blend into the natural background of space. Ice, dust, rock materials already abundant in planetary systems would provide the perfect disguise. To observers with telescopes, the object would appear indistinguishable from the countless small bodies already drifting through space. From that perspective, an interstellar object like 3I Atlas offers an intriguing thought experiment. Its speed is consistent with expectations for debris ejected from another planetary system. Its orbit follows the clean geometry of a hyperbola. The exact path predicted for something entering the solar system from interstellar space. And its glowing coma forms exactly as models predict when frozen material warms under sunlight. Every measurement made so far supports the same conclusion: it behaves like a comet. And yet, the idea that something could perfectly imitate nature has always fascinated scientists and philosophers alike. The most effective disguise is not something exotic or unfamiliar. It is something so ordinary that no one feels compelled to question it. That does not mean 3I Atlas is anything other than what the data indicates: a natural interstellar object. Agencies such as NASA and observatories around the world continue to analyze its trajectory, composition, and activity, and all results remain consistent with known comet physics. But the broader reflection remains compelling. If a technological artifact ever attempted to hide within the immense clutter of cosmic debris, it would likely do so quietly, without dramatic signatures or obvious structures. Ice and dust would conceal it far more effectively than polished metal or visible machinery. In that sense, objects like 3I Atlas remind us how little we truly know about the countless fragments drifting between the stars. Most of them are simply ancient pieces of distant planetary systems, natural relics of cosmic formation. Yet every once in a while, a visitor from interstellar space passes through our solar system and invites a deeper question, not whether it is artificial, but whether we would even recognize the difference if it were. To human observers, comets appear to be harmless wanderers, ancient mixtures of ice, dust, and rock that briefly flare to life when sunlight warms their surfaces. Their glowing tails and irregular behavior are familiar sights in astronomy. They drift through planetary systems as relics of formation, fragments left over from the birth of stars and planets. But in speculative discussions about extraterrestrial intelligence, some researchers have imagined a very different possibility. Instead of broadcasting powerful signals across space, advanced civilizations might rely on quiet observation. This idea is sometimes connected to concepts within the search for extraterrestrial intelligence, where scientists explore how intelligent life might detect or deliberately avoid detection by other civilizations. One related idea is the so-called surveillance hypothesis, the notion that certain interstellar objects could theoretically function as passive observers rather than natural debris. In such thought experiments, probes might be disguised to resemble common cosmic materials so they could enter planetary systems without drawing attention. Objects that already appear chaotic and natural like comets would make especially convincing camouflage. From an astronomical perspective, comets are everywhere. Many originate in distant reservoirs of icy bodies such as the Oort cloud or the Kuiper belt. Others may be fragments ejected from entirely different star systems. Their unpredictable brightness, varied chemical signatures, and irregular shapes are normal features rather than anomalies. Because of this, when astronomers detect a new comet, especially one traveling on an unusual path, the usual response is careful observation and cataloging. Hyperbolic trajectories, high velocities, and unfamiliar chemical compositions are often interpreted as clues about where the object formed. Not as evidence of artificial origin, the interstellar object 3I Atlas fits comfortably within that scientific framework. Its trajectory is hyperbolic. Exactly what scientists expect for a body arriving from outside the solar system. Its speed is high but consistent with objects ejected from distant planetary systems. And its coma, the cloud of gas and dust surrounding its nucleus, forms naturally when solar heat causes frozen material to sublimate. One feature that has attracted interest is its chemical makeup. Early observations suggest carbon dioxide may play a dominant role in its activity compared with water vapor, which is more common in many solar system comets. For astronomers, this is most likely a clue about the environment in which the object originally formed, perhaps a colder or chemically different region around another star. Speculative thinkers sometimes imagine how such variations might be interpreted differently in hypothetical scenarios. If a probe wished to hide among natural objects, unusual chemistry might actually help the disguise rather than reveal it. The diversity already present among comets provides ample room for anomalies that can still be explained through natural processes. Still, it is important to emphasize that there is no evidence suggesting that 3I Atlas or any other known comet is an artificial object. All available observations remain consistent with established models of comet physics and interstellar debris. Yet the thought experiment itself highlights something profound about astronomy. The universe is filled with wandering fragments from distant systems, and each new interstellar visitor offers a brief opportunity to study material formed around another star. Most of the time, those visitors are exactly what they appear to be: ancient debris shaped by gravity and time. But their arrival also reminds us of a deeper truth about exploration when we look out into the cosmos. We are not only searching for answers, we are also learning how to ask better questions. To us, they remain indistinguishable from comets. To them, we might simply be an experiment observed quietly from afar. Of course, the evidence remains firmly on the side of the ordinary. No anomalous signals have been detected. No sudden course corrections reveal hidden propulsion. Every tiny wobble in Atlas's motion can be explained by the gentle push of gas escaping from its surface as sunlight warms the ice. Yet the absence of proof is never the same as proof of absence. If an advanced probe truly wished to remain hidden, broadcasting its presence would defeat the entire purpose. Its survival would depend on blending perfectly into the cosmic background, appearing no different from the countless natural objects drifting through space. In that sense, the surveillance hypothesis is not really about proving alien intent. Instead, it challenges our assumptions. It asks whether we are certain that every object we classify is exactly what we think it is. After all, not every visitor to a planetary system would need to arrive in a blaze of spectacle. Some might prefer silence. Some might rely on patience, measured not in years or centuries, but in thousands or even millions of years. And as Atlas sweeps past the sun and continues its long journey outward, a quiet question lingers behind the data. Was it simply a comet passing through our system, or was it watching us all along? Astronomy often reads chemistry like a language. Each line in a spectrum acts like a syllable. Each ratio between molecules forms a word that helps scientists reconstruct the story of where an object formed and how it evolved. When sunlight strikes an icy comet nucleus, molecules escape into space. As they spread into the surrounding coma, they absorb and emit light at very specific wavelengths. By analyzing that light, astronomers can identify which substances are present. For most comets, the story follows a familiar pattern. Water usually dominates the activity. Alongside it appear traces of carbon monoxide, methane, ammonia, and other simple molecules forged in the cold environments where comets were born. Atlas, however, seems to speak in a slightly different dialect. Early observations suggest that carbon dioxide plays an unusually strong role in its activity compared with what scientists typically observe in many solar system comets. To researchers, this does not necessarily imply anything mysterious. A straightforward explanation is that the object formed in a region of its original planetary system where carbon dioxide ice was especially abundant. In protoplanetary disks, there are boundaries known as snow lines, distances from the star where particular molecules freeze into solid form. Beyond a carbon dioxide snowline, CO2 can condense and accumulate in large quantities, shaping the chemistry of any icy bodies that form there. If Atlas originated in such a region around another star, its unusual composition could simply be a natural signature of that distant birthplace. Perhaps its surface chemistry was slowly reshaped over billions of years by cosmic rays. Energetic particles drifting through interstellar space can alter the outer layers of icy bodies, gradually transforming their composition over immense periods of time. That radiation might create a hardened crust that traps water ice beneath the surface, while allowing carbon dioxide to escape more easily when the object approaches a star. Scenarios like this are entirely natural and consistent with processes scientists already understand. Interstellar objects spend vast stretches of time traveling through environments where radiation, temperature changes, and micrometeorite impacts can slowly modify their surfaces. When they finally encounter a star again, the chemistry we observe may reflect that long and complex history. And yet for some people the thought experiment continues. What if an unusual chemical pattern were not simply the result of formation or radiation, but something intentionally arranged? Encoding information in chemistry would be an extraordinarily subtle method of communication. A probe transmitting radio signals could be detected and intercepted. A spacecraft with visible structures might be photographed and studied. But chemistry blends seamlessly with nature. Astronomers already expect comets to display a wide range of chemical mixtures and unexpected molecular ratios. In that sense, chemical diversity provides the perfect disguise. If meaning were hidden within those ratios, it could easily pass unnoticed because unusual chemistry is exactly what scientists already expect to find in cometary bodies. One can imagine, at least in theory, a civilization that thinks on timescales far beyond human history. Such a civilization might scatter silent messengers throughout the galaxy. Objects designed to survive millions or billions of years as they drift between stars. When one of them finally passed through a developing planetary system, its chemistry could be observed and analyzed by the inhabitants of that system. In speculative scenarios like this, ratios of carbon dioxide to water could form a kind of pattern. Not an obvious message, but something subtle. Perhaps a mathematical sequence hidden within molecular proportions. Perhaps values that mirror universal physical constants. Something that would look random at first glance, yet reveal structure when studied carefully. A repeating numerical relationship might whisper a simple statement across cosmic time. We were here. At present. However, nothing in the observational data suggests anything like that for Atlas. The chemical measurements available so far can be explained through ordinary astrophysical processes, including formation conditions and long exposure to radiation in interstellar space. Still, the exercise of imagining such possibilities reminds us of something important about science. Every observation begins with an assumption about what is normal and what is not. And sometimes the greatest discoveries occur when something small, quiet, and unexpected forces us to question those assumptions. The spectra observed so far show strong carbon dioxide and comparatively weak water. That is unusual, but still within the wide diversity scientists expect from cometary chemistry. The coma behaves exactly as physics predicts. Sunlight warms the surface. Volatile compounds sublimate, and gas expands outward into space, carrying dust with it. No numerical patterns emerge from the measurements. No prime sequences appear in the ratios. No hidden constants reveal themselves in the data. Everything we currently observe can be explained through ordinary processes acting on an icy body that formed around another star. And yet the very act of measuring raises an intriguing philosophical question. If chemistry itself carried a message, would we even recognize it? Our instruments are designed to identify molecules and measure abundances, not to search for meaning embedded in chemical proportions. Perhaps such a signal would appear indistinguishable from natural variation. It might pass unnoticed, interpreted simply as noise within the vast diversity of cosmic chemistry. The safest and most scientifically grounded conclusion remains that Atlas is natural, a fragment of alien geology rather than alien intention. Still, speculation persists because the silence of space leaves room for imagination. In that silence, chemistry can feel like more than frozen gas escaping from ancient ice. It can resemble an alphabet written in the ratios of molecules, waiting for a reader who has not yet learned how to interpret the language. Another idea sometimes enters these conversations. A concept that began in speculative fiction but has influenced real philosophical discussions about extraterrestrial intelligence. It is known as the dark forest hypothesis. The premise is stark. The universe is like a dark forest at night. Every civilization is a hunter moving quietly through the trees. Revealing your location could invite destruction from another unknown intelligence. Remaining silent becomes the safest strategy for survival. Within that framework, silence is not evidence of emptiness. It is evidence of caution. When an interstellar object like 3I Atlas glides through the solar system without emitting signals or performing any controlled maneuvers, the simplest explanation is still that it is a natural comet. Its faint coma glows in sunlight. Its path follows the predictable mathematics of a hyperbolic orbit. Everything about its behavior matches known physics. But the dark forest idea suggests that if intelligence existed on cosmic timescales, it might behave exactly this way. It would not broadcast loudly across space. It would avoid drawing attention. It would pass quietly, indistinguishable from the countless natural objects already drifting between stars. Of course, there is no evidence that Atlas is anything other than an interstellar comet. Astronomical observations strongly support that conclusion. Yet the thought experiment remains powerful because it reframes the silence of the cosmos. Instead of asking why we have not heard anything, it asks a more unsettling question. What if the quiet itself is the message, its mission? In such speculative thinking, would not be to announce itself. It would be to listen, to watch quietly, to blend so perfectly into the natural background of the universe that no one would ever think to question it. In a cosmos where survival might depend on remaining unseen, the most dangerous act could be to speak. That possibility flips our perspective in an uncomfortable way. For decades, humanity has searched the sky for signal. Radio telescopes scan the heavens, hoping to detect a narrow-band transmission, something artificial that would break the cosmic silence. Programs within the search for extraterrestrial intelligence were built around this hope. We have even tried to speak first. Humanity has already sent messages into space. Small attempts to introduce ourselves to whatever might be listening. The Pioneer 10 and Pioneer 11 carry plaques describing humanity and our location in the galaxy. Later, the Voyager 1 and Voyager 2 left the solar system with the famous Voyager Golden Record, a collection of sounds and images intended for any intelligence that might someday find them. These gestures were made with optimism. They assumed that contact between civilizations would be curious, cooperative, perhaps even friendly. But if the universe truly behaved like the scenario described in the dark forest hypothesis, those signals might look very different. Instead of greetings, they could resemble flares in a dark wilderness, revealing the position of a civilization that has not yet learned how dangerous the forest might be. Of course, 3I Atlas is almost certainly nothing more than a natural interstellar comet. Its motion is fully explained by gravity. Its path is hyperbolic. Its closest approach to the Sun remains far from Earth, hundreds of millions of kilometers away. The mathematics of celestial mechanics leave little room for doubt. Yet the presence of such an object inevitably sparks deeper reflection, not about collision or invasion, but about something quieter. Observation. What if the most extreme possibility is not that someone arrives dramatically, but that someone has already been watching for a very long time? What if our planet is already just another entry in the records of an intelligence that never needed to announce itself? The dark forest idea does not provide answers. Instead, it creates a tension that lingers whenever we encounter the silence of space. Silence that can be interpreted as emptiness, or perhaps as restraint. As Atlas curves around the Sun and begins its long departure back toward interstellar space, it may carry nothing more than frozen carbon dioxide and the ancient chemical history of another star system. But its silence invites a different kind of curiosity, because in a forest of stars, silence does not always mean peace. Sometimes silence simply means that no one is speaking, and sometimes it means someone is listening. The unease surrounding Atlas does not come from physics. It comes from imagination. Humanity has been conditioned to fear impacts from space. The history of our planet carries the scars of those events. The Great Crater in the Yucatan marks the collision that ended the age of the dinosaurs. The explosion over Siberia in 1908, known as the Tunguska event, flattened forests across thousands of square kilometers. Popular culture has reinforced that fear, filling films and headlines with visions of fiery comets rushing toward Earth and desperate last-minute attempts to stop them. Because of this, whenever the word comet appears in the news, the first instinctive question is simple and ancient. Is it coming for us? When Atlas was first detected, the same question surfaced almost immediately. Before the orbital calculations were fully refined, some wondered whether this visitor from interstellar space might pose a danger. But the mathematics were clear. The object's path is hyperbolic, and its closest approach remains hundreds of millions of kilometers away. It will pass through the solar system and continue outward into the darkness between the stars. The numbers close the door completely on the possibility of impact. Yet the absence of physical danger does not eliminate the psychological effect of the discovery. Instead, it shifts the focus of curiosity. If the object is not a threat, then what exactly is it? A body of rock and ice that might collide with Earth triggers an immediate and visceral fear. But a body that quietly passes through the solar system is unfamiliar for fictional verbiers, distant, and difficult to explain, invites a different kind of speculation, in a strange way that can feel even more unsettling. Catastrophe is simple. It is dramatic and immediate. A visitor that simply appears, behaves slightly differently from what we expect, and then disappears again, leaves behind a lingering question rather than a clear conclusion. Safety does not always equal comfort when the unknown is involved. Atlas carries that psychological weight because of what it represents. It is only the third confirmed interstellar object ever detected passing through our solar system. Each of these rare visitors offers a direct sample of material formed around another star. Every measurement reshapes what astronomers think they understand about planetary systems across the galaxy. And Atlas already appears unusual even within that small group. It travels faster than earlier interstellar visitors. Its chemistry shows unexpected patterns that researchers are still trying to interpret. Its approach direction suggests it may have originated from an older stellar population somewhere within the Milky Way. None of these features imply danger, but together they remind us that the solar system is not isolated. Every so often, Fragments of distant worlds wander through our cosmic neighborhood, carrying with them stories written long before our planet existed. And when one of those travelers appears in our telescopes, the real impact is not physical. It is the sudden awareness of how vast and mysterious the galaxy truly is. These facts are not dangerous in any physical sense, yet they touch something older in the human mind. Unease often appears when we confront how little we truly understand and how much of the universe still remains hidden in darkness. The collision never comes. Earth continues its quiet rotation. Life moves forward beneath skies that will never blaze with the fire of an incoming impact. And yet within that safety, another kind of disturbance appears. If Atlas is not here to harm us, then why is it here at all? The deeper tension is not the fear of dying, but the uneasy thought of being observed, of being studied, of facing a reality far stranger than we expected. We remain safe, but that safety does not entirely reassure us. The discomfort does not lie in the mathematics of the orbit. It lies in the silence that surrounds it. If current models are correct, Atlas may have been wandering through the galaxy longer than our own solar system has existed. Its velocity, its direction of arrival, and its chemical composition hint that it could have originated in the thick disk of the Milky Way, a population of stars that formed when the galaxy itself was younger and far more turbulent. That possibility makes the object not merely old but primordial. It could be a fragment carrying memories from an era when the cosmos was still assembling its first generations of stars and planets. To call such an object ancient is almost an understatement. If it truly formed 10 or even 12 billion years ago, then Atlas predates Earth, predates the Sun, and predates every ocean, forest, and living creature that has ever existed on our world. When our planet was still nothing more than a swirling cloud of gas and dust, this fragment may already have been traveling through interstellar space, long exiled from whatever star system once gave it birth. From our perspective, the comet appears suddenly, an unexpected visitor entering the solar system in the present moment. But for the object itself, nothing about this encounter is sudden. Its journey may have stretched across geological ages of the galaxy, a silent trajectory unfolding over billions of years. The path that now carries it past the Sun could have been set in motion long before our star even ignited. That realization raises another quiet question in the minds of astronomers and dreamers alike. What launched it? Natural explanations are plentiful. A giant planet in some distant planetary system might have flung it outward through gravitational interactions. A close encounter with a passing star could have torn it free from its original orbit and sent it drifting into interstellar space. Over immense spans of time, the gravitational tides of the galaxy itself can reshape trajectories and scatter fragments between the stars. Whatever the exact mechanism, objects like Atlas remind us that the galaxy is constantly exchanging material. Pieces of one planetary system become travelers that may eventually wander into another. Each such visitor is not merely a comet but a messenger from a place we may never see directly, carrying within its ice and dust the chemical history of another corner of the universe. Over billions of years, gravity does not need urgency. A single close encounter with a massive planet or a passing star can be enough to unbind an object from its home system forever. Once released, it drifts outward into interstellar space, becoming one of the countless fragments wandering between stars. This natural explanation is both simple and powerful. Planetary systems are chaotic places in their youth, and many objects are inevitably scattered outward by gravitational interactions. Yet when we place that natural picture beside the more speculative possibilities, the mystery gains another dimension. If Atlas truly began its journey billions of years ago, then the galaxy it left behind was a very different place. Entire civilizations, if they ever existed, could have risen and vanished during the time this object has been traveling. Worlds may have formed, flourished, and gone dark again while Atlas continued its silent path through the Milky Way. Some speculative thinkers imagine a different possibility. What if the object was not simply thrown outward by chance, but launched deliberately? In such a scenario, it would resemble a message in a bottle cast across the ocean of space. Not necessarily intended for us, but sent outward by minds that hoped some distant civilization might one day encounter it. If that were true, Atlas would not only be a relic of galactic history, it would be a fragment of intention drifting through time. Even without such speculation, the object remains extraordinary simply because of its age. We may be observing matter that formed around a star that no longer exists. The chemistry preserved within its ice could have been shaped under conditions very different from those in our own solar system. Each spectrum astronomers record and each image processed from telescopes becomes more than just a measurement. It becomes a faint conversation across billions of years. Through those measurements, we ask questions into the darkness. The answers arrive only as patterns of light and molecular fingerprints. Yet they still carry stories from places and eras we will never visit. In that sense, an ancient relic has briefly arrived within our reach. Whether it was sent here by random gravitational chaos or by some deeper intention lost to time, it carries with it the weight of deep cosmic history. Watching such an object glide past the sun reminds us how brief our own story truly is. Human civilization occupies only a tiny moment within the vast timeline of the universe. Long before our species existed, fragments like this were already traveling through the galaxy. Long after we are gone, others will continue the same journey. That thought leads to another powerful idea. Imagine technology so advanced and so durable that it survives long after the civilization that created it has disappeared. Machines continuing their missions for millions or even billions of years, wandering from star to star while the voices that once guided them have faded into silence in a galaxy as old as ours. Such relics are not impossible to imagine, whether Atlas is simply ice and dust or something more exotic. Its passage offers the same lesson. The universe is ancient beyond human intuition, and every so often it sends us a traveler that reminds us just how deep that history truly goes. This is the unsettling possibility that sometimes appears in quiet discussions when people look at Atlas. What if it is not only ancient rock and ice, but something like ghost technology? A machine still moving, still operating, still following instructions written billions of years ago by creators who no longer exist. The scale of that idea is almost impossible to grasp. Our own technology shows how difficult such endurance would be. Even the most advanced spacecraft humanity has built struggle to survive a few decades in deep space. Radiation slowly damages electronics. Microscopic dust grains erode surfaces. Power systems degrade. Eventually, the instruments fall silent. Probes like Voyager 1 and Voyager 2 have lasted far longer than anyone expected. Yet even they will eventually lose power and drift quietly through the galaxy as inert relics. But imagination sometimes asks a larger question. What if another intelligence somewhere in the galaxy solved the engineering challenges that limit our own machines? What if they learned how to build systems capable of surviving not for decades, but for millions or billions of years? Structures resistant to radiation, energy sources that function across geological time, guidance systems patient enough to continue their mission even after their creators have disappeared. Seen through that speculative lens, Atlas becomes more than a comet. It becomes a symbol of a different possibility. A relic that behaves perfectly like natural debris, yet might conceal something deeper beneath its icy surface. Its behavior fits every expectation of comet physics. It sublimates under sunlight, forms a glowing coma, and follows the precise rules of celestial mechanics. Nothing about its motion contradicts natural explanations. And yet, if something were designed to hide in plain sight, imitation of nature would be the most effective disguise imaginable. A probe that shines like a comet, drifts like a comet, and releases gas like a comet would pass unnoticed through almost any astronomical survey. Silence would not indicate emptiness. Silence would simply be the strategy. The more haunting possibility emerges when we consider the fate of the civilization that might have built such technology. In a universe shaped by time, every civilization faces risks. Conflict, resource exhaustion, environmental collapse, or simply the slow passing of cosmic ages could erase even the most advanced societies. The galaxy may contain the remnants of countless cultures that rose, flourished, and vanished long before humanity appeared. If something like Atlas were ever engineered, it might not be a messenger awaiting instructions. It might be an orphan artifact, continuing a mission whose purpose has long been forgotten. The machines would still function, faithfully executing programs written by minds that are now only dust scattered among the stars. That possibility shifts the tone of speculation. Instead of imagining threats, it invites reflection about legacy. Ghost technology would mean that civilizations can reach astonishing levels of knowledge and engineering, solving problems we barely understand today, and still disappear completely. What would remain are not cities or voices, but quiet travelers moving through the galaxy, carrying faint traces of a story whose authors are gone. It would suggest that the galaxy might already contain the remnants of intelligence, scattered among the stars as silent artifacts continuing tasks whose original purposes have long been forgotten, even without their creators. Such machines would still communicate something powerful simply through their endurance. Surviving across billions of years would itself be a form of testimony. Evidence not written in language or radio signals, but in persistence. If Atlas is nothing more than natural rock and ice, then it remains remarkable for what it reveals about chemistry and planetary formation across the galaxy. But if we imagine, even hypothetically, that something technological were hidden within such an object, then it would say something equally profound about civilizations themselves. It would highlight both the heights intelligence can reach and the fragility that might ultimately erase those who achieved it. In that distant future, our own creations might follow similar paths. Machines launched by humanity that continue wandering through space long after our civilization has faded. The most unsettling interpretations of Atlas are not about dramatic impacts or violent encounters. They revolve around patience, silence, and strategies unfolding across spans of time far longer than human history. One can imagine an object that looks exactly like a comet and behaves exactly like one, passing through a planetary system without drawing attention, yet within its structure there might exist something else. Microscopic devices, dormant biological material, or self-assembling systems designed to remain inactive for vast periods. Waiting would be central to such a concept. Not waiting for minutes or years, but for centuries or millennia. In speculative discussions, this sometimes appears as the idea of a silent infiltration, where natural-looking debris spreads tiny particles or materials that go unnoticed because they resemble ordinary comet dust. Within those particles could exist microscopic structures capable of surviving extreme radiation and temperature changes while remaining inactive until certain conditions appear. The trigger for such activation is also imagined in many different ways. Perhaps these hypothetical systems would respond to the electromagnetic signals produced by a technological civilization. Perhaps they would monitor atmospheric chemistry, recognizing the presence of industrial gases or artificial radio transmissions as signs that an intelligent species has reached a certain stage of development. Only then would they awaken. Of course, there is absolutely no evidence that Atlas contains anything of this kind. Observations so far show behavior completely consistent with known comet physics. Astronomers studying the object continue to interpret its activity through natural processes such as sublimation, outgassing, and the interaction between sunlight and frozen volatiles. Yet the reason these ideas continue to surface is not because scientists believe Atlas is artificial. It is because objects like this remind us how little we still know about the wider galaxy. A fragment that formed around another star and traveled for billions of years before briefly passing our sun invites imagination as much as analysis. And sometimes the act of imagining possibilities is what pushes science to ask deeper questions about the universe and our place within it. Or perhaps such hypothetical systems would be even more patient, designed to remain inactive until a host world reaches a certain level of development that makes observation worthwhile. In speculative discussions, this idea sometimes appears as a slow cosmic strategy, where tiny dormant components travel unnoticed inside natural debris until the conditions of a planet signal that something interesting is happening. The appeal of that concept lies in its subtlety. Instead of dramatic arrivals or obvious signals, the material would simply ride along with comets and asteroids, spreading across planetary systems, in the same way spores spread through an ecosystem. Most would never reach a planet. Most worlds would remain untouched. But in theory, only one successful encounter with a habitable world at the right moment would be enough for the system to fulfill its purpose. Skeptics quickly point out the enormous physical challenges such a scenario would face. Interstellar space exposes matter to intense cosmic radiation for billions of years. Complex molecules degrade over time. The violent release of gas and dust from a comet as it approaches a star could scatter or destroy delicate structures. Even if some microscopic components survive those hazards, the statistical odds of them reaching a specific planet would be extremely small. Billions of particles could disperse into the vast emptiness between stars, with only a minute fraction ever encountering a planetary environment. Yet speculation of this kind is less about predicting reality and more about exploring possibilities. It asks what patience combined with extremely advanced technology might look like if a civilization were willing to operate on timescales far beyond a single lifetime or even a single species. In that sense, the silent infiltration idea reframes the concept of threat or presence. It imagines something that does not hurry, does not announce itself, and may not even unfold within the timescale of human history. If an object like Atlas carried such a system in a purely hypothetical sense, it could pass through a star system appearing completely ordinary. It might release nothing detectable and continue on its path as just another interstellar fragment. To observers, it would remain exactly what it appears to be: a comet drifting quietly through the solar system. For scientists studying the real object, however, the explanation remains far simpler. Observations continue to show that Atlas behaves like a natural interstellar comet, shaped by the same physical laws that govern countless other icy bodies. Its outgassing, its motion, and its chemical signatures all fit within known models of cometary activity. Still, the existence of objects like this reminds us of something profound. The galaxy is old, unimaginably old, and filled with travelers that have been wandering for longer than human civilization has existed. When one of those travelers briefly passes our sun, it carries not only the chemistry of another star system, but also the invitation to think about possibilities far beyond our current understanding. Decades later, or even centuries later, those hypothetical seeds might awaken. By that time, the memory of the interstellar visitor that carried them would likely have faded. Its path would exist only in archived data and astronomy textbooks, rather than in active observation programs. The object itself would be long gone, continuing its journey through the galaxy, while whatever it left behind remained quietly embedded in soil, oceans, or atmosphere. Of course, this is speculation layered upon speculation. Yet it resonates because it reflects a deeper human fear. The most unsettling possibilities are rarely the loud or obvious ones. They are the events that unfold quietly, unnoticed, long before anyone realizes they have happened. The idea that something significant could occur while we were still simply gazing upward in curiosity captures that anxiety perfectly. There is another aspect of Atlas that also challenges intuition. By the standards of cosmic time, small icy bodies are fragile. Comets are made of loosely bound mixtures of ice, dust, and rock. They erode as sunlight warms their surfaces, releasing jets of gas that slowly strip material away. Tidal forces during close planetary encounters can fracture them. Collisions with dust and debris can gradually break them apart. Over millions of years, let alone billions. Many such bodies should disintegrate into scattered grains, drifting through interstellar space. And yet Atlas appears to have endured. An object perhaps only a few hundred meters across, possibly no larger than a mountain, may have survived a journey stretching back to the early history of the galaxy. That possibility pushes against our intuition about durability. If its origin in the thick disk of the Milky Way is correct, the object may have been traveling long before Earth formed around the young Sun. During that immense span of time, it would have passed through regions filled with interstellar dust, endured radiation from energetic cosmic events, and felt the gravitational influence of countless passing stars. Each of those encounters could have altered its path or destroyed it completely. The galaxy has never been a calm place. Supernova explosions, the stellar winds, and dense molecular clouds create environments capable of reshaping or erasing small bodies. Yet despite those hazards, Atlas has survived long enough to appear in the telescopes of astronomers in the 21st century. After billions of years of wandering, it now glows faintly in reflected sunlight as it passes through our solar system. A small fragment of another star system briefly visible against the darkness of space. Whether it is simply an ancient comet or something far more complex imagined by speculative minds, its existence alone carries a remarkable message. The universe preserves travelers from deep time, from fragments that have crossed unimaginable distances before arriving within reach of our instruments. And sometimes the most extraordinary discovery is not what those travelers are. It is the realization of how long their journey has been. The natural explanations remain strong, though they do not answer every question completely. Perhaps Atlas is simply tougher than most cometary bodies. Its interior may be unusually compact, with volatile layers protected beneath crusts, hardened by radiation over immense stretches of time. Cosmic rays striking the surface for billions of years can gradually transform the outer layers into a protective shell, one that slows erosion and helps preserve the material inside. In that case, Atlas may belong to a rare category of comets capable of surviving far longer than typical icy bodies. Another possibility is that we are underestimating how many such travelers exist. Interstellar space could be filled with ancient fragments wandering silently between stars, most of them too small and faint for our telescopes to detect. If that is true, Atlas would not be an extraordinary survivor, but simply the first member of a vast unseen population that occasionally passes close enough to be observed. Still, speculation sometimes wanders into darker territory. What if the survival of such an object were not entirely natural? Enduring across galactic timescales is extremely difficult for fragile materials. Over billions of years, radiation, impacts, and gravitational disturbances gradually degrade almost everything. For an object to persist intact for so long would require extraordinary resilience. In purely speculative thought experiments, that resilience could suggest design rather than accident. In such an imagined scenario, Atlas might not be merely a comet but a vessel disguised as one. Its battered exterior hiding structures far beyond our technological capabilities. It could be a probe built to survive immense spans of time, wandering automatically through the galaxy long after the civilization that launched it had disappeared. Whether anyone remains to receive its data would no longer matter. The machine would simply continue its mission. Ideas like this highlight the uneasy space between what science can confirm and what imagination explores. Natural survival is entirely possible and consistent with known physics. Yet the concept of deliberate design sometimes feels like a cleaner narrative, because intentional engineering could easily account for extreme durability. If such an interpretation were ever true, the object's survival itself would become a kind of signal, not transmitted through light or radio waves, but written into the simple fact that it is still here. Long before Atlas entered our awareness, another interstellar visitor triggered a similar wave of curiosity. In October 2017, astronomers using the Pan-STARRS Observatory in Hawaii detected a faint object moving along a hyperbolic trajectory. It was later named Oumuamua, a Hawaiian term meaning messenger from afar arriving first. Unlike anything seen before, this object defied easy classification. At first, researchers tried to determine whether it was a comet or an asteroid. It showed no visible coma or dust tail like typical comets. Yet its brightness fluctuated dramatically, suggesting an extremely elongated shape, perhaps 10 times longer than it was wide. Something like a cosmic shard tumbling through space. Then astronomers noticed something even stranger. As the object moved away from the sun, its path changed slightly in a way that could not be explained by gravity alone. The acceleration was small but measurable. That observation launched a wave of scientific debate as researchers tried to determine what natural process might produce such behavior. Normally, small changes in a comet's trajectory can be explained by outgassing. When sunlight warms the surface, gas escapes and produces a tiny thrust that slightly alters the object's motion. But in the case of Oumuamua, astronomers could not detect the usual signs of such activity. There was no visible coma, no clear tail of dust or gas, and yet its motion showed a small acceleration that gravity alone could not explain. The effect was subtle, but precise measurements confirmed that something beyond simple gravitational forces was influencing its path. The mystery deepened when scientists reconstructed the object's trajectory before it entered the solar system. Like later interstellar visitors, Oumuamua followed a hyperbolic orbit with an eccentricity greater than 1. That meant it was not bound to the sun and would eventually leave the solar system forever. It had arrived from interstellar space and would continue its journey back into the galaxy after its brief encounter with our star. Unfortunately, astronomers had only a short window to study it. The object was already moving away rapidly when it was discovered, and within weeks it became too faint for most telescopes to observe. Those limited observations became the basis for years of scientific debate and speculation. Researchers tried to understand what kind of object could produce the unusual signals that had been recorded. Some scientists argued that the explanation might still be entirely natural. Perhaps Oumuamua was a fragment of a shattered planet or an icy body whose more volatile substances had evaporated long before it reached our solar system. Hidden ices such as hydrogen or nitrogen might have been escaping in quantities too small for telescopes to detect directly, producing just enough thrust to alter its motion. Others explored more speculative interpretations. The astrophysicist A.V. Loeb suggested that the object's unusual properties could be consistent with an artificial structure such as a thin solar sail. In that view, radiation pressure from sunlight rather than gas jets could explain the observed acceleration. Although this idea attracted widespread attention, most astronomers consider natural explanations more likely. Years later, the debate remains unresolved because the available data are incomplete. Oumuamua has already traveled far beyond the reach of modern telescopes. We cannot return to observe it again or gather additional measurements. In that sense, it remains a kind of ghost in astronomical research. An object that briefly appeared, raised difficult questions, and then vanished into interstellar space before those questions could be answered. What it left behind was not only a scientific puzzle, but also a shift in perspective. Astronomers realized that interstellar objects pass through the solar system more often than previously believed. Each one carries information about distant planetary systems, and each one may behave differently depending on its origin and composition. So, when a later visitor appeared, moving even faster and showing unusual chemistry, many people immediately remembered that first encounter. Comparisons with Oumuamua resurfaced. Every reassurance that a new object was natural met the quiet reminder that our understanding of interstellar bodies is still incomplete. Not long after Oumuamua, another interstellar object provided a useful contrast. In August 2019, amateur astronomer Gennady Borisov discovered a comet later named 2I Borisov. Unlike its mysterious predecessor, this visitor behaved almost exactly like a textbook comet. It displayed a clear coma and tail, and its chemistry matched what astronomers expected from icy bodies forming around other stars. In that sense, Borisov served as a kind of reassurance. It showed that interstellar objects do not necessarily defy explanation. Sometimes they behave precisely as physics predicts. Yet the memory of Oumuamua continues to shape how scientists and the public think about new visitors. Every time another interstellar traveler enters our solar system, the same quiet question returns. What exactly is passing through our cosmic neighborhood? And how much of it escapes our notice until it has already disappeared back into the dark between the stars? From the moment astronomers calculated its trajectory, there was no doubt that 2I Borisov was also unbound from the Sun. Like the earlier visitor Oumuamua, it had arrived from interstellar space and would eventually leave again, continuing its long journey through the galaxy. But unlike Oumuamua, Borisov carried no puzzling silence and no strange behavior that resisted explanation. Borisov was a comet in every familiar sense of the word. As it approached the Sun, it developed a bright coma. A glowing cloud of dust and gas surrounding its nucleus. A long, luminous tail streamed behind it, visible in telescope images as sunlight caused frozen materials on its surface to sublimate. Everything about its appearance matched what astronomers have observed in comets within our own solar system. Spectroscopic observations confirmed this impression. Measurements revealed water vapor, carbon monoxide, and other molecules commonly found in icy cometary bodies. These chemical fingerprints told a straightforward story. Borisov was a frozen remnant from another planetary system, responding to solar heating exactly the way comet physics predicts. For researchers who had struggled to interpret the strange signals from Oumuamua, this clarity was deeply reassuring. Borisov behaved in a language astronomers already understood. Its activity supported the models, suggesting that many young planetary systems eject icy debris during their formation. Over time, those fragments drift into interstellar space, becoming wanderers that occasionally pass through other star systems. Because Borisov behaved so predictably, astronomers were determined not to miss the opportunity to study it in detail. The Hubble Space Telescope captured images showing the comet's nucleus surrounded by vapor and dust. Observations with the Atacama Large Millimeter Array measured the gases escaping from its surface. Meanwhile, the Very Large Telescope collected polarimetric data revealing the properties of the dust grains in its coma. In each case, the results told the same consistent story. Borisov was natural, ordinary, and fully understandable within existing models of cometary behavior. Yet ordinary in this context did not mean insignificant. On the contrary, Borisov provided something that the earlier interstellar visitor could not offer. It gave astronomers clarity. By behaving exactly as expected, Borisov established a baseline for understanding interstellar objects. It confirmed that other planetary systems likely produce icy comets, similar to those in our own solar system, and that these bodies can survive long journeys between stars. In other words, Borisov showed that the galaxy may be filled with countless such wanderers drifting silently through interstellar space. That realization was important because it transformed a mystery into a broader context. Instead of seeing each interstellar visitor as a unique anomaly, scientists could now begin comparing them as members of a larger population. Borisov demonstrated that at least some of these objects are exactly what they appear to be. Ancient fragments of distant planetary systems briefly visiting our Sun before returning once again to the darkness between the stars. The observations of 2I Borisov suggested something profound. The processes that shape comets in our own solar system likely operate throughout the galaxy. Borisov's chemistry showed diversity, but not anything fundamentally alien. It appeared to be the product of another star's planetary nursery, yet still closely related to the comets that orbit our Sun. In a sense, Borisov became a calm moment between two far more unsettling discoveries. It arrived after the mysterious passage of Oumuamua and before the more puzzling arrival of 3I Atlas. Where Oumuamua left scientists with unanswered questions and Atlas later introduced new uncertainties, Borisov offered reassurance. For a while, it allowed astronomers to believe that interstellar visitors were simply natural debris, fragments ejected from distant systems by the same gravitational chaos that shapes our own. Yet that sense of clarity may have been temporary. The confidence Borisov provided made the next discovery feel even more striking. When Atlas appeared, its properties pushed the conversation into unfamiliar territory again. It was moving faster than either of the earlier visitors, showed unusual chemistry, and might even have originated from a region of the galaxy older than the solar system itself. Suddenly, the discussion was no longer just about observing these objects. It became about interpreting what they might represent. The numbers alone drew attention. Oumuamua had impressed astronomers with its unusual motion, and Borisov confirmed that interstellar comets could behave in familiar ways. Atlas, however, entered the solar system with a hyperbolic excess velocity of roughly 60 kilometers per second. That speed is far higher than what was measured for its predecessors. In celestial mechanics, velocity carries history. The faster an object moves, the more energetic the events that must have shaped its path. One explanation is of violent origin. Atlas could have been expelled from its original planetary system by a powerful gravitational encounter with a giant planet or a nearby star. Such interactions can accelerate small bodies to extreme speeds before ejecting them into interstellar space. Another possibility is endurance. Over billions of years, an object drifting through the Milky Way can experience repeated gravitational nudges from passing stars, slowly altering its velocity until it reaches unusually high speeds. Either scenario implies a long and dramatic history. The velocity alone suggests that Atlas has been shaped by powerful events somewhere in the galaxy. But the chemistry adds another layer of intrigue. While Borisov displayed the familiar mixture of water vapor and carbon-based molecules typical of comets, Atlas appears different. Observations using instruments such as the James Webb Space Telescope have suggested that carbon dioxide dominates its coma in proportions rarely seen in comets from our own solar system. To astronomers, this unusual composition likely reflects the environment where the object originally formed. Different regions of protoplanetary disks contain different mixtures of frozen materials depending on temperature and distance from the star. Yet the ratios observed in Atlas still feel unfamiliar. Almost like a molecular fingerprint written in a dialect, we are only beginning to learn how to interpret. Several natural explanations have been proposed for the unusual properties of 3I Atlas. Scientists consider formation near a carbon dioxide snowline, the possibility of radiation-hardened crusts formed over long exposure to cosmic rays, or thick insulating mantles that trap volatile gases beneath the surface. None of these ideas are impossible. Yet even with those models, the object still appears unusual compared with the comets we know. Its chemical signature does not match the familiar patterns seen among bodies that formed within our own solar system. In that sense, Atlas is alien. Not in the science fiction meaning of artificial design, but in the literal astronomical sense. It represents material that formed under conditions different from those around our Sun. It may have condensed in a protoplanetary disk orbiting another star, where temperatures, radiation fields, and chemical gradients were unlike those that shaped our planetary neighborhood. Age deepens the mystery further. Based on its trajectory and direction of approach through the galaxy, some analyses suggest it could originate from the thicker stellar population of the Milky Way's older disk. If that interpretation is correct, Atlas may have spent billions of years wandering through interstellar space. It could have been ejected from its home system long before Earth even formed oceans. That possibility transforms the object from a simple comet into something closer to a cosmic time capsule. Inside, its frozen material may be preserved chemical traces from an earlier era of our galaxy's history. The Milky Way was a far more turbulent place billions of years ago. When star formation occurred in bursts and gravitational interactions between young systems were common, Atlas might carry fragments of that ancient environment across time. When astronomers compare the three known interstellar visitors, Oumuamua, Borisov, and 3I Atlas, they see a progression that resists simple interpretation. Oumuamua arrived first, leaving scientists with puzzling observations and limited data. Borisov followed with chemistry that looked reassuringly familiar, suggesting that interstellar comets might not be so different from those in our own system. Atlas, however, shifts the scale once again. It moves faster than its predecessors, appears chemically unusual, and may be far older. Each new visitor forces astronomers to reconsider what is typical and what is exceptional among objects wandering between the stars. In this sense, the debate is not just about the object itself. Humans naturally search for patterns and explanations. When something appears improbable, we ask whether it is simply a rare event or a sign of something deeper. Atlas may ultimately prove to be nothing more than a fragment of cosmic debris that happens to pass through our region of space at the right moment for us to observe it. Yet, even if that is the case, it still carries an important message. Outliers often reveal the limits of our understanding. They remind us that the universe does not need to conform to our expectations or our current models. Sometimes the most valuable discovery is simply realizing how much we still have to learn about the space beyond our star. When Oumuamua was first detected, many astronomers believed it might be a once-in-a-lifetime event, a single fragment from another planetary system, briefly passing through our solar system before disappearing into interstellar space. Then, only 2 years later, 2I Borisov appeared, suggesting that such objects might be far more common than previously thought. Now Atlas enters the story. Discovered not merely by chance, but because astronomers had begun actively searching for these visitors from other stars. Each new detection hints that the galaxy may be filled with wandering debris from distant planetary systems. And if that is true, then the objects we have seen so far may only be the beginning. The question becomes unavoidable: why are we seeing more of these objects now? Has the galaxy suddenly begun sending its wanderers through our neighborhood? Or has something changed on our side of the equation? The most likely answer is that the change lies in us, not in the sky. Over the past few decades, our ability to observe the universe has improved dramatically. Telescopes have become more sensitive. Surveys cover far larger areas of the sky. And modern computing allows astronomers to analyze enormous streams of data in real time. Objects that would once have passed unnoticed can now be detected as faint moving points of light against the background of distant stars. One of the most significant advances will come from the Vera C. Rubin Observatory. When it begins full scientific operations, its wide-field survey will repeatedly scan the entire visible sky with unprecedented sensitivity. This continuous monitoring is expected to dramatically increase the number of small moving objects we detect, including visitors from outside the solar system. In other words, the cosmos itself has not suddenly changed. What has changed is our ability to perceive it. For billions of years, interstellar objects have almost certainly been passing silently through the solar system. Their journeys were brief and faint, easily lost among the countless points of starlight. Only now are our instruments powerful enough to notice them. Yet the growing number of discoveries carries a psychological weight that goes beyond simple statistics. A single detection can be dismissed as chance. 2 detections begin to feel like a pattern. By the 3rd, the human mind naturally starts constructing a narrative. The first mysterious object. The second more familiar one. The third unexpectedly strange. Even if the universe has no intention of telling a story, our instincts begin to interpret one. Timing also plays a role. For centuries, humans watched comets streak across the sky, often interpreting them as omens or signs meant for kings and empires. But the faint interstellar visitors we are detecting today are far dimmer and move differently from the bright comets visible to the naked eye. Only with modern instruments could such objects be discovered at all. In that sense, we are a very young observing species. We have only recently begun looking beyond the immediate boundaries of our solar system, with the precision required to detect objects drifting between the stars. These discoveries remind us that we are latecomers to a galaxy that has been evolving for billions of years. Long before Earth existed, planetary systems throughout the Milky Way were forming and destroying small bodies. During the violent birth of planets, enormous numbers of icy fragments and rocky debris were gravitationally ejected into interstellar space. Over cosmic time, those fragments accumulated into a vast population of wandering objects traveling through the galaxy. If our observations continue to improve, we may soon find that these visitors are not rare at all. Instead, the solar system could lie along one of many quiet pathways through which interstellar debris regularly drifts. Some of those objects may look familiar, resembling the comets and asteroids we already know. Others may carry compositions or histories that challenge our current understanding of planetary formation. And as we continue searching, one possibility remains open. Among the countless natural fragments scattered through the galaxy, there may someday appear an object whose origin is far harder to explain. The more carefully we observe the sky, the more the silence of the cosmos will either deepen or begin to reveal something unexpected. Across the galaxy, countless fragments of planetary systems drift through the darkness. Most travel alone for millions or billions of years, never passing close to another star again. A few occasionally slip into unfamiliar stellar neighborhoods before continuing their silent journeys. Only in recent decades have our instruments become capable of detecting such travelers, revealing objects like Oumuamua and 2I Borisov. These discoveries suggest that what we have seen so far may represent only a tiny fraction of the true population. Statistically, models of planetary formation imply that the galaxy should contain enormous numbers of these objects. During the chaotic birth of planetary systems, gravitational interactions often fling asteroids and cometary fragments outward at escape velocity. Over billions of years, these ejected remnants accumulate into a vast background population, drifting through the Milky Way. If even a small fraction of planetary systems behave this way, the total number of interstellar fragments could reach into the trillions. That immense abundance leads to an intriguing thought experiment. If millions or billions of natural fragments wander through interstellar space, then statistically even extremely rare possibilities might exist somewhere within that population. This is where imagination begins to intersect with probability. If technological civilizations have ever emerged elsewhere in the galaxy, even briefly, then it is conceivable that they may have produced artifacts capable of surviving long after their creators disappeared. Such objects would not necessarily resemble the machines we imagine today. Over immense spans of time, exposure to radiation, collisions with dust, and chemical alteration would gradually transform any structure. A probe launched billions of years ago might now appear weathered beyond recognition. Its original engineering could be hidden beneath layers of erosion or chemical change, leaving only subtle traces detectable through unusual composition or structural resilience. This idea highlights a deeper challenge. Determining whether something is artificial becomes far more difficult when the object has been altered by cosmic time. An ancient technological artifact might not look like technology in any recognizable form. Instead, it might appear as an unusually persistent object or one with chemical patterns that seem improbable compared with natural formation processes. At present, we simply do not have enough examples to evaluate such possibilities. With only a handful of known interstellar visitors, including objects like 3I, Atlas astronomers cannot yet build reliable statistical models. 3 detections reveal that such bodies exist, but they do not provide the large dataset needed to distinguish common characteristics from rare anomalies. Real understanding requires numbers. If future surveys detect dozens, hundreds, or even thousands of interstellar objects, patterns will begin to emerge. Astronomers will be able to compare their velocities, chemical compositions, trajectories, and physical structures. Within that broader context, a truly unusual object would become far easier to recognize. In statistical terms, the search resembles looking for a needle in a vast cosmic haystack. But the needle would not necessarily shine or appear obvious at first glance. Instead, it might initially look just like every other piece of straw until careful analysis reveals that its properties do not fit the natural distribution. For this reason, the ongoing search for interstellar visitors is not merely about counting objects. Each new detection improves our understanding of how planetary systems form and evolve across the galaxy. At the same time, it quietly expands the possibility that among countless natural wonders there could exist something fundamentally different. Whether such an object will ever be discovered remains unknown. Yet the act of searching carries profound significance. It means that humanity has reached a point where we can begin exploring not only our own solar system, but also the debris and history of other planetary systems scattered throughout the galaxy. And in that vast population of drifting fragments may lie clues to stories far older than our own world. When the Hubble Space Telescope turned its aging but remarkably precise optics toward 3I Atlas, the first images appeared almost disappointingly ordinary. On the detector, the object looked like many comets observed before it. A faint point of light expanded into a soft halo, a diffuse coma spreading outward like breath on cold glass, with the suggestion of a thin tail stretching away from the sun. For decades, this is exactly how comets have appeared through Hubble's patient eye. Astronomers have catalogued hundreds of similar portraits, dusty halos surrounding small icy nuclei that release gas as they warm. To a casual observer, nothing in those images would seem unusual. It looked like a classic comet, the sort of picture found in textbooks and astronomy archives. Yet astronomers know that the most important clues in such images rarely shout. They whisper, subtle details in brightness, shape, and expansion patterns can reveal the physical processes driving the comet's activity. What looks ordinary at first glance can hide information about composition, structure, and history. The coma surrounding Atlas appeared stronger than expected for an object at that particular distance from the Sun. Normally, comet activity at large distances is driven mainly by the sublimation of water ice. But the brightness and structure of Atlas's coma hinted that more volatile substances, possibly carbon dioxide or carbon monoxide, might be dominating the outgassing instead. Each pixel recorded by Hubble's instruments contains measurable information. Astronomers analyze how sunlight scatters from dust grains, how gas expands outward from the nucleus, and how brightness changes over time. By combining those measurements, researchers can estimate the size of the object, the rate at which material is escaping, and the types of molecules present in the coma. These images therefore represent the most visible public portrait Atlas will ever present to Earth. They show an object that appears both familiar and subtly unusual, something that fits the general behavior of comets, yet carries hints of a different origin. There is also an important limitation to such observations. Even with the extraordinary resolution of the Hubble Space Telescope, astronomers cannot directly see the solid nucleus of most comets. The core remains hidden inside the glowing cloud of gas and dust it releases. What we observe is not the surface itself, but the expanding atmosphere surrounding it. That means the true structure of Atlas, its exact shape, surface features, and internal composition remains concealed. The coma acts like a luminous veil, masking the nucleus from direct view. In this sense, every comet carries an inherent mystery. We observe what the object sheds into space, while the solid body at its center keeps many of its secrets. As the images circulated worldwide, accompanied by careful explanations from researchers, they seem to confirm a reassuring narrative. Atlas looked like a comet, behaved like a comet, and therefore was probably just another comet. Yet the deeper scientific question remained open. Sometimes the most effective camouflage in nature is not invisibility but familiarity. When something closely resembles what we expect, we may stop asking difficult questions. Hubble's photographs show a classic cometary appearance, but within that familiar picture lie subtle details that continue to invite careful examination. There is a certain irony in what the Hubble Space Telescope revealed. One of the most advanced observatories ever placed in orbit produced images that feel almost antique. A bright halo of dust, a soft cloud of gas, a narrow tail stretching away from the sun. It is exactly the picture children draw when they imagine a comet. That familiarity is comforting, because it reinforces the idea that Atlas behaves like the comets we already understand. But familiarity can also be deceptive. Humans tend to trust what looks normal. When an object fits the patterns we already recognize, we rarely question it further. Yet nature sometimes hides unusual phenomena behind very ordinary appearances. In that sense, the images of Atlas function almost like a psychological test. They present something that looks typical, while quietly leaving open the possibility that deeper details might tell a different story. The photographs themselves cannot answer that question. Hubble's view is limited to the visible glow of gas and dust surrounding the comet's nucleus. What lies within that cloud remains hidden. The images, therefore, record only the surface expression of the object, not the structure beneath it. To investigate further, astronomers turn to the James Webb Space Telescope. Webb was designed specifically to study the chemical fingerprints of distant objects by analyzing the infrared light they emit and absorb. Unlike traditional imaging, spectroscopy allows scientists to identify the molecules present in a comet's coma with remarkable precision. When Webb's instruments observed Atlas, researchers expected to see a familiar pattern. Most comets show a mixture dominated by water vapor, along with smaller amounts of carbon monoxide, carbon dioxide, and dust containing silicate minerals. Instead, the spectrum appeared unusual. The signatures suggested a much stronger presence of carbon dioxide relative to water than is typical for comets observed in our solar system. Measurements indicated that carbon dioxide may dominate the escaping gas by a large margin. Ratios on the order of tens of parts CO2 for each part water are far higher than what astronomers commonly observe in nearby comet populations. Such results do not necessarily imply anything artificial, but they do challenge the assumptions built into many existing models of comet formation. At first, the unusual chemistry generated excitement among researchers. Astronomy often advances when observations contradict expectations. Several natural explanations were proposed. One possibility is that Atlas formed near the carbon dioxide snowline of its original protoplanetary disk, a region where CO2 ice could condense more efficiently than water ice. Another idea suggests that cosmic radiation over billions of years altered the outer layers of the nucleus, gradually depleting water from the surface while leaving carbon dioxide trapped within. Dust mantles may also play a role. Thick layers of dust conceal volatile materials beneath the surface, allowing certain gases to escape more readily than others when the object warms. These processes could produce chemical imbalances that appear unusual compared with comets formed around our own sun. However, the scale of the observed ratios remains intriguing. The spectra from the James Webb Space Telescope do more than identify molecules. They reveal how actively those molecules are escaping into space, even at distances where many comets remain relatively quiet. Atlas showed clear signs of activity. Its coma of carbon dioxide extended across enormous distances, forming a cloud hundreds of thousands of kilometers wide. In scientific terms, this behavior suggests a comet rich in highly volatile compounds, likely shaped by formation conditions different from those of most solar system bodies. The observations therefore highlight an important possibility. Objects arriving from other star systems may carry chemical histories unlike anything we typically see in our own cosmic neighborhood. The behavior of 3I Atlas raised another subtle question among astronomers. Activity in comets normally begins when sunlight warms their surfaces enough to sublimate volatile ices. Yet Atlas appeared active at distances where many comets remain relatively quiet. It was releasing gas earlier and more strongly than expected, producing a coma that suggested significant amounts of highly volatile material. For scientists studying such objects, the first step is always to search for natural explanations. Comets formed in colder regions of a protoplanetary disk can contain compounds like carbon dioxide or carbon monoxide that begin to sublimate at lower temperatures than water ice. If Atlas formed in such an environment, its early activity could simply reflect a composition different from the comets that formed closer to our Sun. Still, the data from the James Webb Space Telescope did not fit neatly into familiar categories. Spectroscopic measurements showed unusually strong carbon dioxide signatures compared with water vapor. This does not imply anything artificial, but it does suggest formation conditions unlike those typical of solar system comets. In astrophysics, such anomalies are often the most valuable clues, pointing researchers toward new insights about planetary formation in other star systems. Different researchers interpreted the results in different ways. Some saw them as evidence of exotic yet natural chemistry from a distant stellar nursery. Others emphasized how little we still know about the diversity of comet compositions beyond our own system. In science, unusual data often stimulates debate because it expands the range of possible explanations. What the observations clearly demonstrated is that precise measurements do not always bring immediate understanding. Even with the remarkable sensitivity of the James Webb Space Telescope, the telescope can only reveal what molecules are present and how they behave. Interpreting why those molecules appear in certain ratios requires models of formation, history, and long-term evolution models that are still incomplete. Because of this, Atlas remains defined as much by the questions it raises as by the answers it provides. It reminds astronomers that every new interstellar object expands the range of phenomena we must explain. The galaxy is likely filled with planetary debris formed under countless different conditions, and each new visitor may carry a chemical story unlike the last. Researchers also explored another possibility: whether the object emitted any artificial radio signals. Radio telescopes were directed toward Atlas in the hope of detecting structured transmissions or repeating patterns that might indicate technological activity. These observations are part of the broader scientific effort known as search for extraterrestrial intelligence. The results, however, were consistent with natural expectations. Instruments detected only the background radio noise produced by interactions between solar radiation, charged particles, and the gas and dust surrounding the comet. Such signals are common for active cometary bodies and do not indicate any artificial source. For decades, researchers in the search for extraterrestrial intelligence have confronted a broader puzzle often described as the Fermi paradox. In a galaxy containing hundreds of billions of stars and countless planets, one might expect evidence of advanced civilizations to be common. Yet so far, no confirmed signals of technological origin have been detected. The silence itself has become an object of study. Some scientists argue that intelligent civilizations may be extremely rare or short-lived. Others suggest that technological signals may simply be difficult to detect across interstellar distances. Whatever the explanation, the quiet response from Atlas fits within the pattern. Astronomers have observed for decades the universe continues to reveal natural phenomena that are surprising and complex, even when no artificial signals appear. Silence in astronomy can have many explanations. Often, it is simply the result of distance. Signals weaken rapidly as they spread across space. And even powerful transmissions can fade into undetectable noise after traveling light years. Sometimes the problem may be technological, a signal could exist, but its frequency, encoding, or duration might not match the instruments we use to search for it. This challenge lies at the heart of the search for extraterrestrial intelligence. Radio telescopes scanning the sky typically look for narrow-band signals or repeating patterns that would be difficult to produce by natural processes. So far, despite decades of observation, no confirmed artificial transmissions have been detected. When objects such as 3I Atlas are studied, astronomers sometimes include targeted radio observations simply because interstellar visitors are scientifically interesting targets. These measurements are not based on an expectation of finding technology, but on the principle that unusual objects are worth examining carefully with many different instruments. In the case of Atlas, the radio observations revealed only the background noise expected from natural interactions between solar radiation, charged particles, and the gas escaping from the comet. The absence of detectable signals therefore fits within the broader pattern already known to researchers. Every survey conducted so far has returned the same result: the sky appears quiet. This persistent silence is closely connected to a famous scientific question known as the Fermi paradox. Given the enormous number of stars and potentially habitable planets in the Milky Way, many scientists have wondered why no clear technological signals have yet been identified. Several explanations have been proposed. Intelligent civilizations may simply be rare, emerging only occasionally in the history of the galaxy. Even if they do arise, they might exist for relatively short periods before technological or environmental challenges bring them to an end. Another possibility is that advanced societies communicate in ways we have not yet learned to detect, using technologies beyond the radio methods we currently rely on. Some researchers also note that the detectable window for radio communication may be brief. Human civilization has been emitting strong radio signals into space for just over a century, a tiny fraction of cosmic time. If other civilizations follow similar technological paths, their detectable phase might also be short, making overlap between civilizations extremely unlikely. For these reasons, the quiet response from Atlas does not carry any extraordinary implications. It simply reflects the same observational reality that astronomers encounter whenever they scan the sky for artificial signals. The data are consistent with a natural cometary object traveling through the solar system. Yet the silence still carries meaning in a broader sense. Each observation reminds us that our understanding of the galaxy is still developing. Whether the universe ultimately proves to be full of life or largely silent, the search itself continues to expand our knowledge. Interstellar visitors like Atlas provide rare opportunities to study material from distant star systems and to refine the tools we use to explore the cosmos. Sometimes the universe responds to our questions not with dramatic discoveries, but with quiet ambiguity. The passage of an interstellar object like 3I Atlas illustrates this clearly. The scientific data themselves, orbital parameters, brightness measurements, and spectroscopic signatures are technical and precise. Yet when such discoveries reach the public, they rarely arrive as raw numbers. They are translated into narratives shaped by headlines, images, and the choices of what details to highlight. When news of Atlas spread, the communication challenge appeared immediately. Scientists and institutions had to explain that an object from another star system was passing through our solar system without allowing speculation to turn into unnecessary alarm. Objects like Atlas may sound dramatic, but the actual physics of their trajectories often places them safely far from Earth. Organizations such as NASA typically address this challenge by presenting clear and measured explanations. Their statements focus on orbital mechanics, observational data, and the expected path of the object. In the case of Atlas, the message emphasized that the object posed no collision risk and would simply pass through the inner solar system before continuing on its interstellar journey. These careful statements are important because they provide a factual baseline. Without them, unusual astronomical events could easily become sources of confusion or fear. At the same time, scientific language can feel restrained compared with the dramatic nature of the discovery itself. Media outlets face a different pressure. A headline stating that an interstellar comet is behaving exactly as predicted may not capture public attention. As a result, descriptions often emphasize the most unusual aspects: the speed of the object, the rarity of interstellar visitors, or the unusual chemical signatures detected by instruments such as the James Webb Space Telescope. These details are scientifically accurate, but the framing can sometimes amplify the sense of mystery. The rise of social media adds another layer to this process. Information spreads rapidly across platforms where scientific context is often shortened or simplified. In these environments, fragments of real research can become the starting point for speculation. Some discussions remain thoughtful and grounded in evidence, while others transform the story into something far removed from the original data. Within this environment, an astronomical object can take on many symbolic meanings depending on the audience interpreting it. To some people, it represents a fascinating scientific discovery. To others, it becomes a mystery or even a source of anxiety. These reactions say as much about human curiosity and imagination as they do about the object itself. For scientists, however, the focus remains on observation and evidence. Interstellar visitors like Atlas provide rare opportunities to study material that formed around other stars. Each measurement helps researchers refine models of planetary formation and understand how common such wandering objects might be throughout the Milky Way. In the end, the story of Atlas shows how discoveries in astronomy move through different layers of interpretation. There is the raw data collected by telescopes, the careful explanations offered by researchers, and the narratives that emerge when those discoveries enter the public conversation. Between those layers lies a constant effort to balance curiosity, accuracy, and imagination while we continue exploring the universe. Modern media ecosystems tend to reward the most extreme interpretations. Algorithms on social platforms amplify posts that trigger strong reactions: fear, excitement, outrage, while careful explanations and measured uncertainty often receive far less attention. In science communication, this creates a persistent tension. Nuanced interpretations, which are essential to scientific thinking, rarely compete well against dramatic narratives that promise definitive answers. For researchers studying objects like 3I Atlas, this tension can feel particularly sharp. Their primary responsibility is to the data report what observations show, describe the limits of those observations, and avoid conclusions that go beyond the evidence. Yet scientists are also aware that the way discoveries are framed influences how the public perceives them. If an object is described as entirely ordinary, public curiosity fades quickly and interest in supporting future research may decline. If it is described as mysterious or extraordinary, attention rises, but so can speculation and misunderstanding. Communicating discoveries, therefore, becomes a delicate balance between inspiration and caution. History shows how easily that balance can shift. In 1977, the famous WOW signal briefly sparked speculation about extraterrestrial technology before later studies suggested natural explanations were more likely. In 2017, the interstellar visitor Oumuamua triggered widespread debate because some of its observed properties were unusual and difficult to explain immediately. In both cases, the public narrative often focused on the most dramatic interpretations rather than the cautious conclusions favored by most researchers. This pattern is not necessarily about misinformation. It reflects a natural human tendency. When confronted with something mysterious, people are drawn to stories that feel larger than life. The communication challenge surrounding Atlas reflects the same dynamic. Compressing a billion-year journey through interstellar space into a headline inevitably simplifies the complexity of the science. Explaining unusual chemistry or extreme velocities without encouraging unfounded speculation is equally difficult. In practice, the most honest approach is often to acknowledge the tension directly. Scientific discoveries can evoke wonder and uncertainty at the same time. Observations frequently raise new questions before providing clear answers. And the process of investigation unfolds gradually as more data become available. Astronomers therefore approach objects like Atlas with a mixture of curiosity and skepticism. Skepticism is a foundational principle of science. Unusual claims require strong evidence. So far, every measurable property of Atlas, including its velocity, composition, and radio silence, remains consistent with natural astrophysical processes. Its speed, though high, can be explained by gravitational ejection from a planetary system. Its unusual chemistry may reflect formation in a different region of a protoplanetary disk around another star. And the lack of radio signals matches what astronomers observe for countless natural objects moving through space. In that sense, Atlas serves as a reminder that nature itself often produces phenomena more surprising than our expectations. Many discoveries that initially appear mysterious eventually become understood through careful observation and improved models. The challenge for scientists is to remain open to unexpected possibilities while resisting the temptation to interpret anomalies as something extraordinary before the evidence supports it. And yet, scientific curiosity naturally pushes against the edges of certainty. Atlas is only the third confirmed interstellar visitor ever detected passing through our solar system. Compared with earlier objects such as Oumuamua and 2I, Borisov, it appears faster, chemically unusual, and possibly older. Its trajectory may even suggest origins in older stellar populations within the Milky Way. Individually, each of these characteristics can be explained through known astrophysical processes. High velocities can result from gravitational ejections during the chaotic formation of planetary systems. Unusual chemical ratios may reflect formation in regions of protoplanetary disks where different volatile compounds condensed. Age estimates derived from galactic trajectories can indicate that an object has wandered for billions of years through interstellar space. When combined, however, these details naturally provoke questions. Scientists do not dismiss unusual observations, but they also avoid conclusions unsupported by evidence. Maintaining that balance is central to scientific practice. Rejecting new ideas too quickly can prevent discoveries, while accepting speculative explanations without proof undermines the credibility of the entire field. Astronomy provides many examples of this delicate balance. When pulsars were first detected in the late 1960s, their remarkably regular radio pulses initially led some researchers to jokingly label them LGM signals, short for little green men. Later observations revealed that they were rapidly rotating neutron stars emitting beams of radiation. Similarly, quasars, later understood to be powered by supermassive black holes, once appeared so energetic that their true nature seemed almost impossible to explain within existing models. These historical episodes remind scientists that the universe often presents phenomena that appear mysterious at first. Over time, as observations accumulate and theories improve, those mysteries frequently become understood within the framework of natural physics. For this reason, researchers approach anomalies with curiosity, but also with discipline. The same principle applies to Atlas. Its unusual properties invite investigation, but so far, none of them require explanations beyond natural astrophysical processes. The speed, chemistry, and radio silence observed around the object are all consistent with models of interstellar debris produced during planetary formation. At the same time, the discussion surrounding Atlas touches on broader philosophical questions about life and intelligence in the universe. One of these ideas is sometimes called the Great Filter. The concept suggests that somewhere along the path from simple chemistry to advanced technological civilization, there may exist a difficult step that very few species successfully pass. If such a barrier exists, humanity still does not know where it lies. It could occur early in the development of life, making intelligent civilizations extremely rare. Alternatively, it could appear later, limiting the longevity or expansion of technological societies. Against that cosmic backdrop, objects like Atlas acquire a symbolic dimension. They remind us that the galaxy has existed for billions of years before humans developed the ability to observe it. Material from distant star systems can travel immense distances and carry chemical records of environments far older than Earth itself. Whether Atlas is simply a fragment of ancient planetary debris or part of a much larger population of similar objects, it represents a tangible connection to other regions of the galaxy. Studying such visitors allows astronomers to investigate the diversity of planetary systems beyond our own and to refine our understanding of how those systems form and evolve over cosmic time. In the end, the most important aspect of discoveries like Atlas is not speculation about extraordinary possibilities, but the scientific process itself. Careful observation, open inquiry, and evidence-based reasoning allow researchers to explore the unknown without abandoning rigor. Through that process, each interstellar visitor becomes another piece of the larger puzzle of how our galaxy, and potentially life within it, has developed across billions of years. One way to interpret a discovery like 3I Atlas is purely scientific, a fragment of ice and rock ejected from a distant planetary system long ago, now briefly passing through ours before continuing its journey into interstellar space. That explanation fits everything we currently observe. Yet, objects like this inevitably invite deeper reflection about the broader story of life and civilization in the cosmos. In a philosophical sense, an interstellar object can feel like a kind of testimony. Not testimony in the literal sense of technology or intentional design, but evidence that planetary systems across the Milky Way have been forming, evolving, and sometimes violently ejecting material for billions of years. Each fragment that drifts between stars carries the chemical imprint of environments that existed long before Earth formed. This perspective sometimes intersects with a larger cosmic question: if intelligent civilizations have arisen elsewhere, why have we not seen clear evidence of them? That puzzle is closely related to the Fermi paradox and to a related hypothesis known as the Great Filter. The Great Filter concept suggests that somewhere along the path from simple chemistry to advanced technological civilization, there may exist a stage that is extremely difficult to pass. It could occur early in the development of life, meaning intelligent species are extraordinarily rare, or it could occur later, limiting how long technological civilizations survive before disappearing. Against that backdrop, objects like Atlas can feel symbolic. They are pieces of cosmic debris that have traveled for immense spans of time, possibly billions of years, through interstellar space. Their long journeys remind us how ancient and dynamic the galaxy is compared with the very short history of human civilization. What makes this reflection particularly striking is how ordinary the object appears. There are no artificial signals, no unusual maneuvers, no evidence of technology. Atlas looks exactly like a natural comet, a nucleus of ice and dust surrounded by gas released as it warms near the sun. Everything about its behavior follows known physical processes. Yet that ordinariness carries its own quiet message. Over cosmic timescales, even the most complex structures can eventually erode into simple forms. Radiation, in the first collisions, and chemical reactions gradually reduce objects to basic materials. Ice becomes vapor, rock fractures into dust, and complex arrangements of matter slowly dissolve into simpler states. From that perspective, Atlas reminds us that the universe is governed by immense spans of time. Civilizations, if they arise, may exist only briefly compared with the lifetimes of stars and galaxies. Over billions of years. Even extraordinary achievements could leave behind only faint traces, or none at all. For humanity, this realization functions less as a warning and more as a mirror. Our species is still young on the cosmic timeline. The technologies we use to observe objects like Oumuamua, Borisov, and Atlas have existed for only a tiny fraction of our planet's history. Studying these interstellar visitors therefore serves two purposes. Scientifically, they provide valuable data about the formation of planetary systems beyond our own. Philosophically, they remind us how rare and fragile intelligent life may be in a universe measured in billions of years. When astronomers track Atlas measuring its orbit, analyzing its spectra, and predicting its path through the inner solar system, they are primarily recording the trajectory of a natural object. But they are also participating in something larger, humanity's ongoing effort to understand our place in the vast, ancient cosmos that surrounds us. It is striking that an object like 3I Atlas appears during a period when humanity finally has the tools to detect it. For billions of years, objects of this kind may have been passing quietly through the solar system without leaving any trace in human awareness. Before modern astronomy, even large comets could arrive and depart without detailed measurement, their paths recorded only as brief streaks in the sky. Today, the situation is very different. Modern observatories scan the sky continuously, and automated surveys compare enormous streams of images to detect even faint moving objects. Systems designed to track asteroids and comets now monitor the heavens with a precision unimaginable a century ago. Telescopes on Earth and in space analyze light across many wavelengths, allowing astronomers to measure an object's motion, composition, and brightness in extraordinary detail. Because of these advances, the arrival of an interstellar visitor now becomes a measurable scientific event rather than a fleeting curiosity. Instruments such as the Hubble Space Telescope and the James Webb Space Telescope can study the faint chemical fingerprints in the gas surrounding such objects. Meanwhile, wide-field sky surveys increasingly detect small bodies that would once have gone completely unnoticed. From a scientific perspective, the timing is not mysterious but expected. Models of planetary system formation suggest that enormous numbers of icy fragments and rocky debris are ejected into interstellar space during the chaotic early stages of planet formation. Over billions of years, these fragments accumulate into a vast population of wandering objects drifting through the Milky Way. Given such a population, occasional passages through our solar system are inevitable. What has changed is our ability to see them. As observational technology improves, astronomers expect the rate of discoveries to increase dramatically. Future surveys, especially those conducted by facilities like the Vera C. Rubin Observatory, may detect many more interstellar visitors each year. Human perception, however, often interprets timing through narrative rather than statistics. When something rare appears exactly when we have the ability to observe it, it can feel almost theatrical, as if the universe had chosen a moment for its arrival. This impression arises naturally from the coincidence between technological readiness and the event itself. In reality, such coincidences are a common feature of scientific progress. Discoveries often occur when new instruments open a window that previously did not exist. Radio telescopes revealed pulsars only after their sensitivity became sufficient. Space telescopes allowed astronomers to observe distant galaxies in ways that ground-based instruments could not. Each new capability changes what becomes visible to us. The same principle applies to interstellar objects. For centuries, they likely passed unnoticed because we lacked the tools required to detect them. Now that our observational systems have matured, these travelers from other star systems are beginning to appear in our datasets. Rather than suggesting intentional timing, this moment reflects a transition in human capability. Our species has reached a stage where we can observe phenomena that were always present but previously invisible. Atlas therefore marks not just the arrival of an interstellar object, but the beginning of a new era in which humanity can systematically study material originating far beyond our own solar system. The timing of Atlas's arrival inevitably gives it a symbolic weight far greater than its physical presence. As one of the first confirmed interstellar visitors ever studied in detail, it appears at a moment when humanity is only beginning to develop the ability to observe such objects. Our telescopes now scan the sky continuously. Our detectors measure faint chemical signatures. And our computational systems can track objects moving through vast datasets of celestial images. From a scientific perspective, the timing is most likely the result of probability. Interstellar objects, fragments of planetary systems ejected during the formation of planets, are expected to be extremely numerous throughout the Milky Way. With billions or trillions of such fragments drifting between stars, some inevitably pass through the solar system. Only recently, however, have our instruments become sensitive enough to detect them reliably. Yet human perception rarely experiences such events purely through statistics. When something rare appears at the exact moment we are capable of noticing it, the coincidence can feel almost purposeful. The event seems to arrive precisely when we are ready to interpret it. Even though the underlying explanation may simply be the natural intersection of technology and probability, objects like Atlas therefore become mirrors reflecting how humans respond to uncertainty. The scientific response focuses on measurements, orbital trajectories, brightness curves, and chemical spectra gathered by instruments such as the James Webb Space Telescope. These observations help researchers determine the object's composition, origin, and behavior as it moves through the inner solar system. Public reaction, however, often follows a different path. When the discovery of Atlas was announced, organizations such as NASA emphasized a clear and reassuring message: the object posed no threat to Earth and would pass safely through the solar system. Such statements are a standard part of scientific communication, intended to prevent unnecessary concern about celestial objects that might sound alarming in headlines. Despite these reassurances, curiosity and anxiety frequently emerge together when something unfamiliar appears in the sky. Human psychology evolved in environments where approaching objects could signal danger. So uncertainty naturally triggers heightened attention. Even when experts explain that an object is harmless, the instinctive response to the unknown can still produce speculation. In modern digital environments, this speculation spreads quickly. Online discussions transform fragments of scientific information into a wide range of interpretations. Some discussions remain thoughtful and grounded in evidence, while others imagine possibilities far beyond what the data supports. Within these conversations, Atlas has been described as everything from an ordinary comet to something far more mysterious. These reactions reveal something important about human curiosity. When confronted with an unknown phenomenon, people often construct narratives to give meaning to the event. Those narratives can reflect hopes, fears, or cultural expectations about life beyond Earth. In that sense, the stories surrounding Atlas tell us as much about ourselves as they do about the object itself. Fear and curiosity, after all, are closely related responses to uncertainty. Both arise when something challenges our existing understanding of the world. For scientists, the goal is to transform that uncertainty into measurable knowledge through observation and analysis. For the broader public, the same uncertainty can inspire imagination, debate, and reflection about humanity's place in the universe. In this way, Atlas functions not only as a scientific discovery, but also as a psychological lens. By studying how we interpret such events, we learn something about our collective expectations and concerns. The object itself may simply be a fragment of ancient planetary debris drifting through space. Yet the questions it raises highlight humanity's ongoing effort to understand the cosmos and our role within it. Speculation surrounding objects like Atlas often reveals more about human psychology than about the object itself. When people imagine possibilities such as hidden probes, biological seeds, or silent observers watching from afar, those ideas reflect familiar themes in human culture: curiosity about whether we are alone, anxiety about unseen threats, and the deep desire for connection with something beyond our world. Many of these interpretations are inspired by broader concepts that circulate in scientific and philosophical discussions about extraterrestrial life. One well-known idea is the dark forest hypothesis, which imagines a universe where intelligent species stay quiet to avoid attracting attention from unknown rivals. While intriguing as a thought experiment, such ideas remain speculative and are not supported by observational evidence. What the Atlas story illustrates is how easily cultural narratives can grow around a scientific discovery. Astronomers track the object through careful measurement, its position in the sky, its speed, the gases escaping from its surface. Meanwhile, society interprets the same event through metaphors, stories, and imagined scenarios. Headlines, discussions online, and conversations in everyday life become part of a broader social response to the unknown. These reactions highlight a paradox in how humans think about the universe. On one hand, there is a strong desire to discover signs of life or intelligence beyond Earth. On the other, there is an equally strong fear of what such discoveries might mean. When an unfamiliar object appears, curiosity and apprehension often emerge together. From a scientific standpoint, however, the explanation for Atlas remains grounded in physics. Its motion through the solar system follows well-understood gravitational dynamics. Astronomers calculate its trajectory using the laws first described by Isaac Newton and later refined through the work of Albert Einstein. These calculations allow researchers to determine where the object came from and where it will go next with remarkable precision. The measurements show that Atlas follows a hyperbolic path, an orbit that passes through the solar system only once before continuing back into interstellar space. Such trajectories are exactly what astronomers expect for objects that originated around other stars and were later ejected into the wider galaxy. Spectroscopic observations also reveal the gases released from the object's surface as it warms in sunlight. Instruments like the James Webb Space Telescope analyze these emissions to identify molecules such as carbon dioxide, water vapor, and other compounds commonly found in cometary material. Taken together, these measurements show that Atlas behaves like a natural comet formed in another planetary system. Its unusual properties, such as high velocity or distinctive chemical ratios, likely reflect the conditions in the distant environment where it originally formed rather than anything artificial. In this way, physics provides a steady framework that balances imagination. Mathematical models and observational data allow astronomers to separate speculation from evidence. While the arrival of an interstellar visitor can inspire dramatic narratives, the underlying reality is governed by predictable forces, gravity guiding its path, sunlight releasing gases from its surface, and time carrying it onward through space. Atlas therefore reminds us that the universe often appears mysterious, not because it hides deliberate messages, but because we are still learning how to read the natural processes written across the cosmos. In the end, the motion of Atlas is not a mystery to astronomers in the way headlines sometimes suggest. Its path through the solar system can be calculated with remarkable precision. Once enough observations are gathered, scientists determine its orbit and refine that orbit repeatedly as new measurements arrive. Each update reduces the uncertainty until the trajectory becomes extremely reliable. Organizations such as the Minor Planet Center publish these updates continuously. Their bulletins list the orbital elements that define the object's motion, its inclination, eccentricity, velocity, and closest approach to the Sun. With every new observation, those numbers become more precise, much like a steady pulse check, confirming that the calculations remain accurate. From those calculations, astronomers can determine several key milestones in the object's journey. They can predict exactly how close it will come to the Sun, when it will reach that point known as perihelion, and how its path will curve outward again as it leaves the solar system. In the case of Atlas, these calculations show a clean hyperbolic trajectory. That means it is not gravitationally bound to the Sun and will not return after its passage. This predictability is one of the quiet strengths of celestial mechanics. The motion of objects in space follows the same physical principles described by the laws of gravity developed by Isaac Newton and later refined by Albert Einstein. Whether the object is a planet, a moon, or a comet arriving from another star system, those equations apply in the same way. Even the small irregularities in a comet's motion can be accounted for. Jets of gas escaping from the surface create tiny pushes that slightly alter the trajectory, a process known as outgassing. Sunlight itself exerts a faint pressure that nudges small particles outward. Astronomers include these influences in their models, allowing them to track the object's path with impressive accuracy. For the public, orbital diagrams offer a unique kind of reassurance. When the future path of a celestial object can be drawn years in advance, uncertainty gives way to clarity. The curves plotted on those diagrams show no sudden turns, no unexpected maneuvers, only the smooth arc predicted by physics. In that sense, the seemingly wild journey of Atlas is actually part of a much larger cosmic choreography. Its high speed reflects energy gained long ago, likely during a gravitational encounter in another planetary system somewhere within the Milky Way. After that event, it began a long voyage through interstellar space until its path intersected briefly with our solar system. Physics does not remove the wonder from such events. Instead, it frames that wonder within a system of laws that remain consistent across billions of years. The same gravitational principles guiding Atlas today also shaped the formation of planets, the motion of galaxies, and the evolution of the universe itself. There is also a humbling element in this predictability. Humanity can calculate the comet's path with extraordinary precision, but we cannot influence it. We observe, measure, and understand. Yet the object continues on its course regardless of our presence. Perhaps that is the deeper reassurance provided by astronomy. In a universe that often appears vast and unpredictable, certain principles remain stable. The equations governing motion, gravity, and energy continue to apply. Whether the object is a familiar comet from our own solar system or a traveler arriving from the distant reaches between the stars. In reality, the motion of Atlas remains governed by well-understood physical laws. Every observation collected so far confirms that the object follows a hyperbolic trajectory through the solar system. That means it arrived from interstellar space, will swing around the Sun once, and will then continue outward again, never returning. Astronomers refine this trajectory constantly using new observations. Organizations such as the Minor Planet Center update the orbital parameters as additional data arrives. Each update narrows the uncertainty further until the predicted path becomes extremely precise. The calculations show no deviations from what celestial mechanics predicts. Gravity from the Sun dominates the motion, while smaller influences such as radiation pressure from sunlight or tiny thrusts from gas escaping the comet's surface introduce only slight perturbations. These forces are well known and can be incorporated directly into orbital models. Because of this, astronomers can predict the object's closest approach to the Sun perihelion, its speed, and its exit trajectory with remarkable accuracy. The path traced by Atlas is exactly the sort of hyperbolic curve expected for a fragment that was ejected long ago from another planetary system somewhere within the Milky Way. Speculative ideas sometimes imagine more elaborate possibilities, hidden probes, fragments left behind, or deliberate disguises. Such ideas arise naturally when something unfamiliar appears in the sky. However, none of the observational evidence supports those interpretations. The object's brightness, gas emission patterns, and motion all match what astronomers observe for natural comets composed of ice, dust, and volatile compounds. In astronomy, the key test for unusual claims is whether the data require them. So far, Atlas behaves exactly as a natural interstellar comet would be expected to behave. Its gradual fading as it moves away from the sun, its expanding cloud of gas and dust, and its steadily predictable motion all align with standard physical models. That does not remove the sense of wonder surrounding its journey. Atlas likely spent billions of years drifting through interstellar space before crossing paths with our solar system. During that time, it may have passed near other stars, experienced subtle gravitational nudges, and traveled distances almost impossible to imagine. When it finally leaves our region of space, it will simply continue that journey. The same gravitational laws that guided it here will carry it onward again, back into the dark between stars. Future civilizations, perhaps orbiting distant suns, might someday observe it passing through their own skies, just as we have briefly observed it in ours. In this sense, Atlas is not a messenger or a probe, but a traveler shaped by cosmic history. Its presence reminds us that planetary systems throughout the galaxy continuously exchange material through gravitational interactions. The solar system is not isolated. It occasionally encounters fragments of other star systems drifting through the vast structure of the galaxy. And perhaps the most remarkable aspect of the story is this: for the first time in human history, our species has developed the technology needed to notice such visitors. By measuring their motion and chemistry, we are beginning to read the history written into objects that formed around distant stars long before Earth itself existed. What if every question we ask, every headline we write, every signal we send into the void is already part of the experiment? Not because Atlas is a machine, but because the way we respond to the unknown reveals something about us. When something unfamiliar enters our sky, we begin measuring. We analyze spectra, calculate trajectories, publish papers, but alongside the science, something else unfolds. Speculation, curiosity, fear. Every reaction becomes a kind of data, not about the object itself, but about the species observing it. A civilization capable of sending probes across interstellar distances would not need to act dramatically. It would not need to announce its presence. All it would have to do is watch. The debates among scientists, the headlines in the media, the conversations at dinner tables, the signals we send into space hoping someone might answer, all of it would reveal our technology, our psychology, our fears, and our hopes. If that were the case, then silence would not be a failure to communicate. It would be a choice. Atlas glows faintly in our telescopes, trailing a cloud of gas and dust like countless comets before it. Yet the most powerful signal may not be coming from the object at all. It may be flowing in the opposite direction, not in radio waves, but in human behavior. Because the moment we discovered it, we began revealing ourselves. We revealed how quickly we measure, how quickly we speculate, how quickly we worry, and how deeply we long to understand the universe around us. In that sense, the distinction between natural and artificial almost stops mattering, because the presence of Atlas has already done something remarkable. It has made us think, it has made us question, and it has reminded us that every time something new appears in the cosmos, we learn just as much about ourselves as we do about the universe. The phrase worst-case scenario usually brings dramatic images. Impacts. Explosions. Civilizations ending beneath falling skies. But with Atlas, that possibility disappeared almost immediately. The orbit is clean. The distance is safe. The mathematics is clear. There will be no collision. No catastrophe. Just a silent visitor passing briefly through our cosmic neighborhood before continuing its journey into the dark between the stars. And perhaps that is the most fascinating outcome of all. Because sometimes the greatest discoveries are not the ones that threaten us. They are the ones that remind us how small we are, how curious we are, and how much we still have to learn. So Atlas will come, it will sweep around the sun, and then it will leave again, returning to the vast interstellar night it came from. And long after it fades from our telescopes, one quiet question may remain. Not what Atlas was, but what its arrival revealed about us. Sleep well tonight. The universe is still full of mysteries. And somewhere, far beyond our sun, another traveler may already be on its way. It will not strike us. But the absence of physical danger does not close the question. Instead, it sharpens it. Perhaps the worst case was never about rocks and trajectories at all. Perhaps it was about what we would have to confront in ourselves once the object appeared. Because the danger of Atlas lies in what it makes undeniable. We are no longer dealing with abstractions. For generations, the possibility of interstellar wanderers was theory. A line in computer models. A probability whispered in scientific journals. Now they are real. And they are arriving with unsettling frequency. Oumuamua first startled us. Borisov reassured us. And Atlas has unsettled us again. The pattern alone is enough to stir unease. If the galaxy is filled with such travelers, then the question of their nature can no longer be pushed aside. And that question leads directly to the two possibilities we fear most. The first is that we are not alone. That one of these wanderers, perhaps Atlas itself, may carry within it intention. Not a comet, but a device. Not a relic, but a message. The thought thrills and terrifies in equal measure. If we are observed, then we are vulnerable. If we are contacted, we may not survive the encounter unchanged. The silence of Atlas offers no reassurance. Because silence can be strategy. If the object is more than dust and gas, then perhaps it already knows more about us than we know about it. The worst case here is not invasion, but exposure, the realization that we are being studied patiently and invisibly. The second possibility is darker still, that we are alone. That Atlas is nothing but debris, as natural as any comet, and that every interstellar visitor we will ever detect will tell the same story. That the galaxy is littered with fragments, but not with voices. That civilizations either never rise or never last. In this scenario, Atlas becomes a reminder not of company, but of silence, of absence. And if absence is the truth, then the filter that silenced others may yet await us. So the comet drifts past, and the sky does not fall. But in its wake, the weight of realization lingers. Perhaps the real danger was never the impact that never comes. Perhaps it is something quieter, something harder to face. The possibility that knowledge itself can be unsettling. The knowledge that somewhere, something might be watching us. Or perhaps the even stranger possibility that no one is. In that uncertainty, the universe becomes a mirror, not reflecting alien civilizations, but reflecting us, our curiosity, our fears, and our endless need to understand what lies beyond the thin shell of our small blue world. Atlas passes silently through our sky, leaving behind no message, no signal, no sign of intention. Just ice, dust, gravity, and questions. And maybe that is enough. Because in the quiet space between what we observe and what we imagine, something uniquely human begins to emerge. We wonder. We speculate. We search for meaning in the darkness between the stars. Perhaps that has always been the true story of exploration. Not the certainty of answers, but the courage to keep asking. And somewhere, far beyond our sun, another traveler may already be drifting through the galaxy, a fragment of another system, another silent messenger crossing the vast ocean of interstellar space. One day, it too may pass through our sky. Until then, the universe remains patient, vast, quiet, waiting. So tonight, as Atlas continues its long journey back into the darkness between the stars, we are left with the most human task of all, to wonder, to imagine, and to hope that when the next messenger arrives, it will bring not fear, but understanding. Sleep well beneath the stars. The universe is still speaking. We are only just beginning to learn how to listen.